Hello there, and welcome to the Cosmographer. There may be a version of you, hidden in the mathematics of quantum theory, that will never experience its own death. That is not a ghost story. It is one of 10 ideas on this list, and every single one of them begins in real, respected science before it quietly turns cold. Tonight we will walk past the barrier that may explain why the night sky is so silent, the reason some thinkers believe every civilization that speaks is eventually silenced, and a bubble of rewritten physics that could be crossing the universe toward us at the speed of light, with no warning possible. Each idea is a little larger than the one before it. And the theory at the very top of the list rests on a single influence that makes up more than 2/3 of everything that we have measured directly and that we still cannot name or explain. 10 theories, 3 hours, one slow walk to the edge of what physics allows. Get comfortable and let yourself settle in. If this is your first time here, subscribe to the Cosmographer and stay a while. Because by the end of this list, the quiet of the night sky may sound like something else entirely. Now, let's begin at number 10. Number 10. Quantum immortality and the many worlds interpretation. There is a particular kind of idea that only physics can produce. It does not arrive as a ghost story or a warning. It arrives as a line of reasoning, a set of equations followed patiently to their conclusion, and only at the end do you notice that the place the reasoning has taken you is somewhere you did not want to go. The 10 ideas on this list are all like that. Each one begins in ordinary, respectable science. Each one is built from real theories, real measurements, and real open questions that scientists study with a straight face. And each one, when followed to its edge, opens onto something colder and stranger than most people ever hear said out loud. This is not a haunted house. Nothing here is designed to make you jump. These are the quiet ideas, the ones that keep a curious person lying awake long after the lights are out, turning the thought over and finding no easy way to set it down. We are going to walk down all 10 of them slowly, from number 10 to number 1, and the list will descend as it goes, from the personal and the peculiar toward the total and the cosmic. By the end, we will be standing at the possible end of everything. But we begin much closer to home. We begin with a theory about you, and about whether you can ever truly die. To understand the first idea on the list, we have to start with one of the strangest and most respectable interpretations in all of physics. It is called the many worlds interpretation of quantum mechanics, and it was first written down by a young physicist named Hugh Everett III in 1957. Everett was a graduate student at Princeton, working under the physicist John Wheeler, and he was troubled by a problem that had bothered thoughtful people since the earliest days of quantum theory. The problem is called measurement. Quantum mechanics is the most successful theory in the history of science. It describes the behavior of the smallest pieces of the world with a precision that no other theory can match. But at its core, it says something peculiar. Before you look at a small quantum system, the theory does not describe it as being in one definite state. It describes it as being in a blend of many possible states at once, a smear of possibilities that the physicists call a superposition. An electron is not simply here or there. It is described by a wave that covers all the places it could be, each with its own likelihood. And then you measure it. You look. And when you look, you find the electron in exactly one place. The smear of possibilities seems to vanish, and a single outcome remains. The standard textbook picture calls this the collapse of the wave function. Before the measurement, many possibilities. After the measurement, one. But the theory never quite explains how or why that collapse happens, or what counts as a measurement in the first place. It is stitched on by hand, an extra rule bolted onto an otherwise seamless mathematics. Everett's proposal was radical in its simplicity. He suggested that we take the mathematics completely literally and throw the extra rule away. Suppose the wave function never collapses at all. Suppose that when a measurement happens, every possible outcome simply occurs. The electron is found on the left, and it is also found on the right, and the person doing the looking splits along with it. In one branch of reality, a version of the scientist sees the electron on the left. In another branch, an equally real version sees it on the right. Reality does not choose. Reality branches, endlessly, at every quantum event, into a vast and ever-growing tree of parallel outcomes. This is the many worlds interpretation. It sounds like science fiction, and for years it was treated as an embarrassment. But it has a quiet appeal that has kept it alive for more than half a century. It requires no mysterious collapse, no special role for the observer, no extra machinery. It simply says the equations mean what they say. Today, a substantial minority of serious physicists take it seriously, including figures like David Deutsch, who has built parts of his life's work on it. It is not a fringe belief. It is one of the leading candidates for what quantum mechanics is actually telling us about the world. Now we can build the unsettling idea on top of it. The idea is usually called quantum immortality, and it is most often associated with the physicist Max Tegmark, who in the late 1990s described a sharp version of it that he called quantum suicide. It is a thought experiment, not an experiment anyone should ever perform, and the reasoning goes like this. Imagine any situation in which you might die, in which the outcome depends, even slightly, on some quantum event. In the many worlds picture, reality branches. In some of the branches, the event goes one way and you die. In other branches, however improbable, the event goes the other way and you survive. Now ask a careful question. From your own point of view, from the inside of your own experience, which branch do you find yourself in? In the branches where you died, there is no you left to have a point of view. There is no experience there, no one to notice the outcome, no awareness to register that anything happened at all. Experience can only continue in the branches where you are still alive to have it. And so, the argument runs, from your own subjective perspective, you never experience the branch in which you die. You only ever find yourself, moment after moment, in one of the branches where you somehow survived. To everyone else, watching from their own branches, you are simply gone. But from the inside, your awareness threads its way, again and again, into the improbable timeline where you are still here. Follow that thought forward, and it grows stranger still. Consider what quantum events actually are, and how many of them there are. Every radioactive decay, every measurement in a laboratory, every tiny interaction at the smallest scale is a branch point. They are not rare. They happen constantly, everywhere, all the time. Over a single second, the tree of branches grows past any number worth naming. Over a human lifetime, it grows past the point where language has words for the size of it. And in that unimaginably vast tree, the argument says, there is always some branch, however faint, in which you did not die. However thin the thread, it is never quite cut. Let me stay with what this would mean, told from the inside, because it is the part that stays with people. Picture a life lived along that thread. You would pass through decades. Somewhere in those decades, you would face the accidents and illnesses and ordinary dangers that end most lives. And in your own experience, you would survive every one of them, not because you are lucky in the ordinary sense, but because the versions of you that did not survive are no longer present to tell the tale. Each close call would prune away most of the versions of yourself and leave your awareness stranded in the one that continued. The people you love would age, and in your branch they would die. their own awareness presumably continuing along their own threads, in branches you can no longer reach. And you would go on, into ever thinner and more improbable versions of the world, growing steadily more alone with every branch point survived. This is the quiet horror of the idea. It is not death that it makes strange. It is the possibility that the one exit every living thing assumes it has, the ordinary certainty that experience eventually ends, might, from the inside, never actually arrive. Not as a blessing. Not as heaven. Just as a thread of awareness that cannot find the branch where it stops, wandering into stranger and lonelier country with each passing year. Now, it is important to be honest about where the science ends and the speculation begins, because that honesty is what separates this from a ghost story. The many worlds interpretation is respectable. Quantum immortality is not a prediction that the interpretation makes. It is a philosophical extension, and most physicists who take many worlds seriously do not accept the immortality corollary at all. There are good reasons for their doubt. The whole argument leans on the question of how we count probabilities across branches, on what is called the Born rule and the measure problem, which asks how much weight each branch really carries. Those questions are genuinely unresolved, and many physicists regard quantum immortality as a misreading of them rather than a true consequence. Whether subjective experience actually follows the surviving branch is, moreover, something that can never be tested from the outside. To anyone watching, a person simply lives or dies like anyone else. The claim is only ever about the view from the inside, and the inside is the one place no experiment can reach. There is something worth pausing on in the story of Hugh Everett himself, because it tells you how these ideas travel through the world. When Everett finished his thesis in 1957, the reception was cold. The reigning authority on quantum mechanics at the time, Niels Bohr, and the circle around him, found the idea of endlessly splitting realities distasteful, and Everett's work was largely ignored. Discouraged, he left academic physics almost entirely. He went to work on military operations research, on the mathematics of nuclear strategy, and he spent the rest of his career far from the field he had quietly upended. He died in 1982, in his early 50s, without seeing his idea vindicated. He had asked, reportedly, for his ashes to be thrown out with the trash, a last dry joke from a man who took a certain bleak amusement in the universe. It was another physicist, Bryce DeWitt, who revived the idea in the 1970s and gave it the name we use today, the many worlds interpretation. DeWitt was struck, as many people are, by the sheer weight of the picture, the thought of countless copies of himself splitting off at every moment. And slowly, over the following decades, what had been an embarrassment became a contender. It was never proven because by its nature it makes the same laboratory predictions as its rivals, but it stopped being ridiculous. That is the pattern worth noticing. An idea that sounds absurd is followed patiently by careful people, and one generation's embarrassment becomes the next generation's serious question. Quantum immortality rides on the back of exactly that respectability. It is the shadow the serious idea casts when you hold it up to the light at a certain angle. Let me slow down here and put you inside the thought, because the abstract version and the felt version are two different things. Imagine you are the one on the thread. You do not feel immortal. Nothing about your days feels strange. You simply notice, over the years, that you have been fortunate in ways that are hard to explain. The accident that should have been the end of you was somehow not. The illness that took others your age somehow spared you. You are grateful, at first, in the ordinary human way. But the pattern continues past the point where gratitude makes sense. The rooms you sit in grow quieter. The names you knew belong to people who are gone. You are always the one who remains, in every close call, on the far side of every odds, and the world around you thins into a version of itself where your continued presence is the single least likely thing in it. You are not in pain. You are not anywhere dramatic. You are simply still here, once again, in a reality that has quietly rearranged itself around the fact that you did not stop. That is the picture the mathematics permits, and it asks for no ghosts and no magic to draw it. So we leave it as what it is. A cold corner of one of the most serious ideas in physics, reached by taking that idea completely at its word. It earns its place at number 10 not because it is likely, but because the path to it is paved with real equations, and because the destination is a quiet, personal kind of unease that is hard to shake once you have seen it. The mathematics does not care whether we find its conclusions comfortable. It only follows itself, wherever that leads, and it is under no obligation to lead somewhere we would have chosen. It helps to see how this interpretation handles the most famous puzzle in all of quantum mechanics, the one people know even when they know nothing else about the subject. It is the puzzle of the cat. The physicist Erwin Schrödinger described it back in 1935, and he meant it as a criticism, a way of showing how strange the theory becomes when you take it into the everyday world. Imagine a cat in a sealed box, along with a device that will release a poison if a single radioactive atom decays. The decay is a quantum event, a matter of pure chance. Before you open the box, quantum mechanics describes the atom as being in a blend of both states at once, decayed and not decayed. And if the atom is in both states, then the device is both triggered and not triggered, and the cat, absurdly, is described as both alive and dead at the same time. In the standard picture, opening the box forces the choice, collapses the blend, and leaves you with one outcome, a living cat or a dead one. But the many worlds interpretation says something cleaner and stranger. It says there is no collapse. When you open the box, reality branches. In one branch, you find a living cat, and there is a version of you who is relieved. In another branch, equally real, you find a cat that has died, and there is a version of you who is saddened. Both happen. Both versions of you are real. Neither is the true one, because there is no single true one anymore. You have simply become two, each unaware of the other, each certain that the outcome they see is the only thing that occurred. Take that picture and apply it not to a cat, but to yourself, in a moment of genuine danger, and you have the whole engine of quantum immortality laid bare. In the branches where the danger takes you, there is no version left to notice. In the branches where it does not, there is. And your awareness, whatever it is, finds itself only where there is awareness to be found, which is always and only among the survivors. The reason careful people resist the conclusion, even those who accept the branching, comes down to a subtle and unresolved matter of how the branches are weighted. Not all branches are equal in the mathematics. Some outcomes are far more likely than others, and the theory encodes that difference in what it assigns to each branch, a kind of measure or weight. The survivor branch, in a genuine catastrophe, is a branch of vanishingly small weight, a thread so thin that many physicists argue it should barely count at all in any honest accounting of what you should expect to experience. The claim that awareness simply hops onto that thread, regardless of how little weight it carries, may be a misuse of the very rules that make the theory work. That is the mainstream objection, and it is a strong one. The immortality corollary may be less a discovery than a confusion about how probability lives inside a branching world. But notice that even the objection does not dissolve the unease entirely. It says the surviving branch is unlikely, almost weightless. It does not say the branch is empty. And a branch that is real, however thin, is a place where a version of you goes on. The mathematics does not close the door. It only makes the corridor beyond it very narrow and very dark, and leaves the question of who walks down it precisely where it found it, which is unanswered. But if the self becomes unfamiliar when we look at it closely enough, the sky becomes stranger still when we look up. Because when we turn our instruments outward, toward all those hundreds of billions of stars, and listen for anyone else who might be out there, we hear something we cannot explain. We hear nothing at all. And that silence is the doorway to the next idea on the list. Number 9. The Great Filter. In the summer of 1950, a group of physicists were walking to lunch at the Los Alamos National Laboratory in New Mexico. Among them was Enrico Fermi, one of the most formidable minds of the 20th century, the man who had built the first nuclear reactor. The conversation, as they walked, had drifted to flying saucers and the possibility of life among the stars, the sort of things serious people discussed lightly and then set aside. They sat down. The talk moved on to other matters. And then, in the middle of the meal, out of a silence, Fermi looked up and asked a question that has never really been answered. He said, "Where is everybody?" It sounds like a simple thing to ask. It is not. Behind those 3 words sits one of the deepest puzzles in all of science, and it comes from doing a little arithmetic and taking the result seriously. Consider the numbers. The universe is 13.8 billion years old. Our galaxy alone, the Milky Way, contains something on the order of 100 billion stars, and we now know that most of those stars have planets. Beyond our galaxy, there are hundreds of billions of other galaxies, each with its own vast census of stars and worlds. The universe has had an enormous amount of time and an almost incomprehensible number of places in which life might arise. And here is the part that makes the silence strange. Our own galaxy is not that large, measured against the time available. If a single civilization anywhere in the Milky Way developed the ability to travel between stars, even slowly, even at speeds we can already imagine, it would take only a few million years to spread across the entire galaxy. A few million years sounds long, but against the age of the galaxy it is the blink of an eye. The galaxy is old enough for this to have happened not once but many times over. By any reasonable accounting, the Milky Way should be full. The sky should be busy with the signs of others. Space should be, in some form, inhabited and obvious. Instead, we look and we find nothing. We have listened for radio signals for decades. We have scanned the skies for the heat and light of distant engineering. We have examined the atmospheres of other worlds for the chemical fingerprints of life. And so far, every measurement comes back the same way, with silence. This mismatch between how crowded the universe ought to be and how empty it appears is called the Fermi paradox, and it has haunted the people who think about it for 3/4 of a century. There are many possible answers, and we will meet the darkest of them a little later on this list. But one particular answer has a special weight, because it does not simply explain the silence. It turns the silence into a warning about ourselves. That answer is called the Great Filter. The idea was given its name and its sharpest form by an economist and scholar named Robin Hanson in 1996. The reasoning is this. Think of the entire path from lifeless chemistry to a galaxy-spanning civilization as a long series of steps. Dead matter has to become simple life. Simple life has to become complex life. Complex life has to become intelligent. Intelligence has to develop technology. Technology has to survive long enough and grow capable enough to reach across the stars. Each of those is a step, and the whole road runs from a barren rock to a presence written across the sky. Now, somewhere along that road, the reasoning goes, there must be at least one step that is extraordinarily hard to pass. A barrier so difficult, so unlikely, so deadly, that almost nothing that starts the journey ever completes it. That barrier is the great filter. It is the reason the galaxy is quiet. Countless worlds may begin the climb, and nearly all of them fail at the same wall, and so the stars stay silent because almost nothing ever gets past it. The filter is the missing explanation for the empty sky. And here the idea does something that few ideas in science do. It turns around and looks back at us. Because the truly important question is not whether the filter exists. The important question is where it sits. Is the great filter behind us, or is it still ahead? Consider the hopeful version first. Suppose the hardest step, the great improbable barrier, is somewhere in our past. Perhaps the origin of life itself is the near impossible event, the leap from chemistry to the first living thing, so unlikely that it almost never happens anywhere. Or perhaps the barrier is the jump from simple cells to complex ones, the kind of cell that plants and animals are built from, a transition that on Earth took billions of years and may have happened only once. If the filter is one of these early steps, then we are among the rare survivors. We have already passed the great test. The road ahead is open, and the galaxy is ours to inherit, empty and waiting, because almost nothing else ever made it this far. That is the comforting reading. But the evidence, when we look at it honestly, points the other way, and this is where the idea grows sober. Life on Earth appeared astonishingly early. Almost as soon as the planet had cooled enough to hold liquid water, life was here. That suggests the origin of life may not be so hard after all. From there, complex cells arose, and then many-celled creatures, and then intelligence, and then, in a geological instant, technology. Looking back along our own history, we cleared each supposed hurdle with a kind of ease. None of the steps behind us looks like an almost impassable wall. Each one, difficult as it was, we passed. And that apparent ease is the bad news. It is the coldest turn in the whole argument. If none of the hard steps lies behind us, if we passed them all without the universe having to strain, then the great improbable barrier has not yet been faced. It is not in our past. It is in our future. Somewhere ahead of every civilization that climbs this far, there waits a step that almost none survive. Some challenge, some threshold, so reliably fatal that it silences nearly everyone who reaches it, and leaves the galaxy quiet, not because life is rare, but because life that reaches our stage does not last. We do not know what such a barrier would be. We can only guess. Perhaps it is the tendency of a civilization to destroy itself once it grows powerful enough to do so, through its own weapons, or its own mistakes, or some technology whose danger it does not see until too late. Perhaps it is something we have not yet imagined, a wall that only becomes visible from the far side of where we now stand. The honest position is that we have exactly one example of a civilization at our stage of development, and that example is ourselves. With a single data point, we cannot tell whether we are early, whether we are lucky, or whether we are simply next in a long line of others who came this far and went no further. There is a strange twist to this reasoning that the philosopher Nick Bostrom once pointed out, and it captures how the logic inverts our ordinary hopes. Suppose one day we send probes to Mars, or to the icy moons of the outer planets, and we find life there, even simple microbial life, life that arose independently from our own. Most people would greet that as wonderful news, proof that we are not alone. But Bostrom argued, only half in jest, that it would be among the worst news we could receive. Because if life arises easily, springing up on two worlds in one small solar system, then the early steps are not the filter. Life is common. And if life is common and the sky is still silent, then the filter that silences it must lie later, on the road ahead, waiting for everyone. In that light, the emptiest, most lifeless Mars is the most reassuring one. The barren universe is the one that lets us hope the hard part is already behind us. This is why the Great Filter earns its place on the list. It is not a monster or a catastrophe you can point to. It is a piece of reasoning that takes the ordinary silence of the night sky and reads in it a possible verdict on our own future. The stars overhead may not be empty because we are special and alone. They may be empty because we are ordinary, and because ordinary is not enough to last. The quiet of the universe in this reading is not peace. It is the sound of everyone who came before us, all the civilizations that once looked up at their own silent skies and asked Fermi's question, and did not survive long enough to answer it. It is worth appreciating just how carefully people have tried to put numbers to this problem, because the effort reveals how deep the puzzle runs. In 1961, the astronomer Frank Drake wrote down what is now called the Drake equation, a way of organizing the question of how many communicating civilizations might exist in our galaxy. The equation is not a way of getting an answer, really. It is a way of laying out our ignorance in an orderly fashion. It multiplies together a chain of factors, the rate at which suitable stars form, the fraction with planets, the fraction of those planets where life arises, the fraction where life becomes intelligent, the fraction that develops technology able to send signals, and finally, the length of time such a civilization survives and stays detectable. Each factor is a thing we can estimate for the first few and can only guess at for the rest. And the last one, how long a technological civilization lasts, is the great unknown that the Great Filter speaks directly to. The point of the equation, for our purposes, is that even under modest, reasonable guesses, the galaxy ought to be humming with signals. Frank Drake himself put the idea into practice that same era, pointing a radio telescope at nearby stars in 1960 in a project called OSMA, the first real search for extraterrestrial intelligence. In the decades since, that search has grown enormously in reach and sophistication. We have listened across many frequencies, for many years, with instruments of steadily increasing power. And the overwhelming result, with only a scattering of unexplained and unrepeated curiosities, has been quiet. The equation says the sky should be full. The telescopes say it is empty. The Great Filter is one attempt to close that gap, and it closes it by proposing that the last factor, survival, is the killer. Let me spend a moment on the candidates for a filter that lies ahead, because they are what give the idea its edge. If the barrier is in our future, what could it be? One obvious candidate is the tendency of a civilization to gain, all at once, the power to destroy itself. A species that learns to split the atom, or to reshape its own biology, or to build minds greater than its own, acquires in a very short span the means of its own undoing, long before it has acquired the wisdom to be sure of surviving them. Another candidate is subtler, a civilization that does not blow itself up, but simply exhausts or destabilizes the world that sustains it, quietly, through the very growth that made it powerful. And there may be filters we cannot name at all, dangers that only become visible from a stage of development we have not yet reached, waiting past a threshold we cannot see beyond. What makes all of this genuinely sobering, rather than merely interesting, is the arithmetic of the single example. We are one civilization. We have no others to compare ourselves against, no way to know whether our path is typical or rare, safe or doomed. When you have a sample of exactly one, you cannot tell whether you are looking at the rule or the exception. And so we are left in a strange position, gazing up at a silence that might be the most important message we have ever received, a message with no words in it, telling us only that of everyone who came this far before us, none is speaking now. There is one more turn to the Great Filter that deepens rather than lightens it, and it concerns our own moment in time. If the hard barrier really does lie ahead, then our species is standing, right now, at the approach to it, without knowing what it is or when it comes. Every generation before us cleared the steps that lay behind. Whatever the filter ahead may be, we have not yet reached it, which means we are among the countless who arrive at this stage, full of confidence, looking back at a history of obstacles overcome, and mistaking that history for a promise about the future. The unsettling possibility is that the sense of having made it, the feeling that the hard part is behind us, is exactly the feeling that every civilization has just before it meets the wall that stops it. This gives the idea a strange moral weight, because it turns a piece of cosmology into a question about how we choose to live. If the filter is ahead, then it is not fixed like a law of nature. It might be a choice, or a series of choices, a threshold that a wise and careful civilization could, in principle, pass, and that a careless one would not. In that reading, the silence of the sky is not only a warning but almost a challenge, a quiet statement that the ones before us failed at something, and an open question about whether we will do the same. We cannot know what the test is, but we can notice that we are the kind of civilization that has, in a very short span, acquired the power to end itself, and has not yet acquired the certainty that it will not. And there is a gentler thought folded inside even this, worth holding alongside the sober one. It is possible that we are simply early. It is possible that the universe is still young, that the great age of life and intelligence lies ahead rather than behind, and that the silence we hear is the silence of a party that has not yet begun, rather than one that has already ended. In that reading, we are not the last survivors of a filter, but among the first arrivals, looking out at an empty room that will one day be full. The evidence does not tell us which of these is true. It only tells us that the room, for now, is quiet, and leaves us to decide what to make of the quiet. But there is another way to read the silence, and it is darker still. The great filter imagines that the others failed. It is worth noting before we move on that reasonable scientists genuinely disagree about how empty the sky really implies things to be, and the disagreement is instructive. Some hold to what is called the rare Earth view, the idea that while simple life may be common, the particular chain of accidents that led to complex, intelligent, technological life may be so improbable that we are effectively alone, and that there is no filter ahead because there was never anyone else to be filtered. Others argue the opposite, that the ingredients of life are so widespread and the universe so vast that life of some kind must be common, which sharpens the paradox and pushes the filter back toward our own future. The honest truth is that we cannot yet settle the argument because we have found life exactly once, here, and a single instance can support almost any story. Until we find a second example or confirm its absence across many worlds, the great filter will remain what it is, a frame for our ignorance rather than a measurement, and its most important number, the odds of a civilization surviving its own youth, will remain unknown. The next idea imagines that the others are still out there, listening, and that the silence is not failure at all. It is strategy. Number 8. Time crystal civilizations. To understand the 8th idea on the list, we have to begin with something that sounds, at first, like it cannot be true. In 2012, the physicist Frank Wilczek, who had already won a Nobel Prize for his work on the forces inside the atom, proposed a new form of matter. Not a new material, not a new particle, but a genuinely new kind of thing, one that had never been described before. He called it a time crystal, and when he first laid out the idea, it looked as though it broke one of the oldest rules in physics. Think about an ordinary crystal for a moment, the kind of thing a grain of salt or a diamond is. What makes it a crystal is that its atoms are arranged in a repeating pattern in space. Walk along the structure in any direction, and the same arrangement comes around again and again, regular and predictable. A crystal is a pattern that repeats across space. Wilczek asked a strange and beautiful question. If matter can arrange itself into a pattern that repeats in space, could matter also arrange itself into a pattern that repeats in time? A pattern that repeats in time would mean a system that returns to the same state over and over, on its own, forever, moving in a steady rhythm without anything driving it and without running down. And that is where it seemed to break the rules. Everything we know about energy says that a system left alone settles into its lowest energy state and stops. A pendulum swings, but friction slows it, and it comes to rest. A spinning top wobbles and falls. Perpetual motion, motion that never ceases and never costs anything, is the classic impossible dream, ruled out by the laws of thermodynamics. And yet here was a respected physicist describing a structure that, in its very lowest energy state, its most settled and stable form, would still be in motion, ticking through a cycle endlessly, without spending any fuel to do it. For a few years it remained a theoretical puzzle, argued over in papers, refined and reshaped. The original version ran into objections, and the idea was adjusted into a form that could actually exist, what physicists call a discrete time crystal, a system gently nudged by an outside rhythm that then responds with a rhythm of its own, slower and stubbornly regular, one the nudging never quite dictates. And then, in 2016 and 2017, something remarkable happened. Separate teams of physicists actually built them. One group, led by Christopher Monroe at the University of Maryland, used a chain of ytterbium ions, atoms held in place and manipulated with lasers. Another group, working in the laboratory of Mikhail Lukin at Harvard, used a very different system, the flaws and defects inside a diamond. Two completely different approaches, two completely different materials, and both saw the same signature. They saw a system that kept its own time, ticking at a rhythm that the driving force did not impose, holding a beat that came from within its own structure. It was the fingerprint of a genuinely new phase of matter, and it was real. Within 5 years of being imagined, the time crystal had gone from a claim that looked impossible to an object confirmed in more than one laboratory, on more than one continent. Now, it is important to be clear and calm about the scale of these things. The time crystals we have built are tiny, delicate, and fragile. They are quantum systems held together in carefully controlled conditions, not clocks you could hold in your hand. Wilczek's discovery is astonishing, but it is astonishing in the way that a subtle and profound piece of physics is astonishing, not in the way of a machine you could switch on at home. What we have confirmed is that matter can, under the right conditions, break the symmetry of time itself and hold a rhythm forever without cost. That much is solid ground. And now we step off that ground, carefully, and into speculation, because this is where the eighth idea earns its unsettling reputation. The confirmed physics ends here. What follows is extrapolation, an idea that people have proposed, not a prediction that the science makes, and it is only fair to keep that line bright. Some thinkers have asked a further question. If matter can be organized to keep time forever, could a sufficiently advanced civilization learn to organize information that way, and even, in some far reach of possibility, organize a mind that way? Could a civilization encode itself, its memory, its awareness, into structures that exist along the dimension of time, rather than merely traveling through it the way we do? The suggestion is that such beings would not be creatures moving forward moment by moment, as we are, but something more like standing patterns spread across a stretch of time, present at every point of it at once. Nothing in physics requires this to be possible, and there is no evidence that consciousness can be built from time crystals or anything like them. But the idea is worth sitting with, not because it is likely, but because of what it would imply if it were true, and because of the quiet strangeness it opens up. Consider what it would mean to be a being organized along time. You and I experience the world one moment after another. The past is gone, fixed and unreachable. The future has not arrived. We stand always at a single moving point, the present, and we can only ever see the one frame of the film that is playing right now. But a being spread across time would not be trapped that way. To such an entity, a span of history would not unfold. It would simply be there, complete, the way a whole photograph is there for us to look at all at once, rather than developing before our eyes. Every moment of a stretch of time would be equally present to it, laid out together, a finished shape rather than a passing sequence. Let me put you inside that perspective for a moment, because it is the part that unsettles people. Imagine something that could regard the entire history of our species the way you might look at a single long photograph laid flat on a table. Not watching it happen, but seeing all of it together, the beginning and the middle and the end held in one glance. Such a being would not have to wait to learn how our story turns out. Our rise and our ending would already both be visible to it, present in the same moment, complete. Whatever becomes of us, it would have already seen. And it would carry no suspense about our fate, because for it there is no suspense, only a shape that is already whole. We would be, to such an observer, not a drama still being written, but a thing already finished, examined at leisure, its ending as plain and settled as its beginning. We have no way to detect such a thing. If beings like this existed, organized in a way our instruments are not built to notice, they could be regarding us at this very moment, and we would have no means of knowing. Our whole civilization might be as visible to them as a photograph is to us, and they might be as invisible to us as the person holding the photograph is to the faces inside it. What remains, when the speculation is set aside, is the confirmed physics, and even that is strange enough to keep. We have made matter that keeps perfect time forever, in its lowest state, without spending energy, overturning a symmetry of the universe that everyone assumed could never be undone. That is real, and it was confirmed within our lifetimes. The rest, the observers spread across time who might already have seen how everything ends, is a question the science merely makes it possible to ask, and then leaves hanging in the dark. To feel why the confirmed physics alone is so strange, it helps to understand what the scientists actually mean when they say a time crystal breaks a symmetry. The universe is full of symmetries, and they are among the most important things in all of physics. A symmetry simply means that something looks the same when you change your point of view in a certain way. An ordinary crystal breaks a symmetry of space because it picks out particular positions, particular spacings, where its atoms sit, rather than being the same everywhere. And it turns out that the smooth, featureless flow of time has its own symmetry too, the fact that, at the deepest level, one moment is much like another. A time crystal breaks that. It picks out a particular rhythm, a preferred beat, and settles into it, so that its lowest energy state is not still and featureless but moving, ticking, returning to itself over and over. Nobody had thought that the symmetry of time could be broken in the ground state of a system, and Wilczek's insight was to see that it could. The teams that built the first ones had to be clever about it, and the story of how they did it is a small triumph of modern physics. A perfectly isolated system, left alone, tends to heat up and smear out any delicate pattern, which is one reason people doubted a true time crystal could last. The solution was to use systems that resist that smearing, systems where disorder locks the pattern in place, and to nudge them gently and repeatedly from the outside. The chain of ytterbium ions in Christopher Monroe's group and the nitrogen defects scattered through diamond in Mikhail Lukin's both did the same essential thing. They were driven at one rhythm, and they answered back at another, slower rhythm of their own, one they held stubbornly, even when the driving was varied. That stubborn, self-chosen beat was the signature everyone was looking for. It was matter keeping its own time. It is genuinely worth holding on to the ordinary wonder of that before reaching for the speculation, because the real thing is astonishing enough. We are so used to the idea that motion costs energy, that anything moving must eventually stop, that a system moving forever in its most restful state sounds like a contradiction. And yet, in a careful and limited way, that is exactly what these laboratories produced. Not a machine, not perpetual motion of the useful kind that could drive anything, but a quiet, self-sustaining rhythm woven into the structure of matter itself, confirmed and reproduced. The universe, it turns out, permits patterns in time as well as patterns in space, and we did not know that until a decade ago. Only now, with the real thing firmly in hand, is it fair to wander into the speculation and to mark it clearly as speculation. Nothing in the confirmed physics says that time crystals can be scaled up, or made large, or strung together into anything that thinks. The leap from a laboratory rhythm to a mind organized along time is enormous, and there is no evidence for it whatsoever. It is a what-if, an idea people find irresistible precisely because the underlying physics is so unexpected. But what-ifs are allowed, as long as we do not mistake them for findings, and this one leads somewhere worth glimpsing. There is a reason the notion of a being that perceives all of time at once is not quite as alien to physics as it first sounds, and it is worth pausing on, because it comes from Einstein rather than from speculation. In the theory of relativity, time is not the universal, flowing thing our intuition insists it is. It is woven together with space into a single fabric, and different observers, moving differently, disagree about what counts as now, about which events are simultaneous, about the order of things that are far apart. This has led many physicists to a picture sometimes called the block universe, in which past, present, and future all exist together, equally real, laid out as a single unchanging whole, and in which the passage of time, the sense that the present is special and moving, is something to do with us, with how we experience the block, rather than a feature of the block itself. Einstein himself once wrote, consoling the family of a friend who had died, that the distinction between past, present, and future is only a stubbornly persistent illusion. If that picture is right, and it is a serious reading of our best theory of space and time, then in some sense the whole history of the universe already exists, complete, and our experience of living through it moment by moment is a feature of our own limited vantage, not of reality at large. We are like a narrow beam of light moving along a strip of film that is, in its entirety, already there. The speculation about time crystal beings simply asks what it would be like to be something that is not confined to the moving beam, something spread along the whole strip at once, for which the future is not a mystery to be awaited, but a region already present, already visible. The physics does not say such a thing can exist. But it does say that the block itself, the whole of time laid out together, may be the deeper truth, and that our sense of a single fleeting present may be the illusion, not the other way around. That is a quietly disorienting thought to sit with. It means that the future, including our own, may not be open in the way we feel it to be, may not be a blank waiting to be written, but a place that, from a wide enough vantage, is already there. We cannot see it, and we cannot reach it, and for us it makes no practical difference, since we must still live forward, one moment at a time, deciding as if the next page were unwritten. But the physics leaves the door ajar, and the eighth idea simply asks what might stand on the other side of it, looking back through, at a story that for us is still unfolding, and for it is already whole. And if something could see the whole of time at once, could hold our beginning and our ending in a single view, then it is worth asking a harder question about the reality we take for solid ground. What if that ground is not the base layer at all? It is worth grounding all of this before we leave it, in the fact that time crystals are not merely a curiosity that physicists made once and set aside. They are now an active area of research, studied in laboratories around the world, and there is genuine interest in whether their stubborn, self-sustaining rhythms might be useful, perhaps as a way of storing quantum information reliably, since a pattern that holds its beat, despite disturbance, is exactly the kind of thing a delicate quantum computer needs. In other words, the strangest confirmed physics on this list is also, quietly, becoming practical, moving from the realm of astonishment toward the realm of engineering. That is often how the deepest discoveries go. They arrive looking like paradoxes, and within a generation they are tools. So the eighth idea leaves us with two things held side by side. On one hand, a real and useful and thoroughly confirmed piece of physics, matter that keeps its own time forever without cost, now being turned toward practical ends. On the other, a speculation that this same principle, carried far past anything we can build, might permit forms of being utterly unlike our own, observers for whom time is not a river, but a landscape. The first is science. The second is a question the science leaves open, and cannot answer, and cannot quite close either. What if the world we stand on is itself something that could be paused, or altered, or switched off? That is the doorway to the next idea. Number 7. The simulation argument, and simulation decay. The seventh idea on the list is one you have almost certainly heard named, usually in passing, usually as a joke. The suggestion that we might be living inside a computer simulation has become a piece of popular culture, a shrug and a raised eyebrow. But the serious version of the idea is not a shrug. It is a careful piece of philosophy, laid out in 2003 by the philosopher Nick Bostrom, and its power comes from the fact that it is genuinely difficult to escape. It does not ask you to believe anything strange. It only asks you to follow a piece of counting, and then it closes the doors behind you, one by one. Bostrom's argument does not claim that we are living in a simulation. That is the first thing to understand about it, and the thing most people get wrong. What it claims is subtler and harder to shake. It says that at least one of 3 statements must be true, and that we cannot comfortably reject all 3 at once. Here are the 3. The first possibility is that almost every civilization like ours goes extinct before it reaches the technological maturity needed to run high-fidelity simulations of conscious minds. In other words, the ability to simulate whole realities is a stage that almost nobody survives to reach. The second possibility is that civilizations do reach that stage, but that almost none of them ever choose to run such simulations. For whatever reason, ethical, practical, or simply lack of interest, the mature civilizations decline to build simulated worlds full of thinking beings. And the third possibility is the unsettling one. If civilizations both survive to maturity and do choose to run such simulations, then we are almost certainly living inside one. The strength of the argument lies in the third branch, and it comes down to counting. Suppose that running a fully realistic simulated reality, one containing minds that experience their world exactly as vividly as you experience yours, becomes possible for an advanced civilization. And suppose that at least some of those civilizations choose to do it. If they run such simulations at all, they will not run just one. A civilization with that kind of power would run them in enormous numbers, thousands, millions, more, for research, for history, for reasons of their own. Each of those simulations could contain billions of conscious observers. Now do the arithmetic. If simulated minds vastly outnumber the small number of original biological minds in the one base reality, then a randomly chosen conscious being is far more likely to be one of the many simulated ones than one of the few real ones. Not certainly, just far more likely, by sheer weight of numbers. and you are a randomly chosen conscious being. You have no special evidence that you are the rare original rather than one of the countless copies. So, if the third branch is where reality lands, then the honest conclusion is that you are probably simulated. There is no mysticism in this. There are no glitches in the code required, no red pill, no crack in the sky. There is only counting, and counting is hard to argue with. That is the whole engine of the simulation argument, and it is why serious people take it seriously. You can escape the conclusion, but only by accepting one of the first two branches, and each of those carries its own weight. To reject the third, you must believe either that almost everyone destroys themselves before reaching such power, which is a bleak thing to believe, or that almost every advanced civilization looks at the possibility of creating simulated worlds and, without exception, declines. Neither escape route is comfortable. That discomfort is the point. Now we come to the part that gives this entry its place on a list of the coldest ideas in science, because it is possible to take the argument one step further into darker territory. Suppose we grant, for the sake of the thought, that we might indeed be simulated. What follows from that? What follows is a dependency, and it is total. If our reality is a simulation, then our entire existence rests on the continued interest, the continued resources, and the continued stability of whoever or whatever is running it. And a simulation is not a permanent thing. A simulation can be paused. It can be edited. It can be slowed down when resources run short. It can be switched off. The beings running it might face their own difficulties, their own shortages of power or time or patience. They might reallocate their computing capacity to other purposes, the way a researcher shuts down one experiment to make room for another. They might simply lose interest in this particular run, the way anyone eventually loses interest in a project that has served its purpose. And if they do, there would be no warning to us, no sign, no chance to prepare. One instant the world would exist, whole and detailed and full of history. The next instant it would not, closed like a file, the way an experiment ends when the person running it has learned what they wanted to learn. Some have taken the idea further still, into the search for evidence, though it must be said plainly that this part is speculation and not established in any way. If we lived in a simulation, the reasoning goes, might there be signs of the underlying machinery, seams where the construction shows? People point to certain features of physics and wonder. The speed of light is an absolute limit that nothing can cross, and one could read that, if one were determined to, as something like a processing constraint, a maximum speed built into the system. The strange, grainy, discrete nature of the quantum world, the way certain quantities come only in fixed smallest amounts, could be read as the resolution limit of a simulation, the smallest step the underlying calculation can take. These readings are not evidence. There is no reason to think the speed of light or the quantum of action are anything but fundamental features of a real universe. But the fact that the idea can be entertained at all is part of why it lingers. Let me put you inside the feeling of it for a moment, because the abstract argument and the lived sensation are different things. Imagine standing on a floor you have trusted your whole life, solid stone, the most reliable thing you know. And imagine slowly realizing that you cannot actually prove it is stone. That it might be a surface, convincing in every detail, resting on nothing you can see or reach or verify. Nothing about the floor would change. It would feel exactly as solid as before. But the certainty underneath it would be gone, replaced by the quiet awareness that the ground of everything might be, not bedrock, but someone else's attention. And attention is the one thing in all of experience that has never, anywhere, been guaranteed to last. We should be fair about the limits of all this. The simulation argument cannot be tested by any means we currently accept. There is no experiment that distinguishes a perfect simulation from a real world, which is precisely what makes it philosophy rather than physics. And the idea of simulation decay, of the plug quietly pulled, is speculation built on top of speculation, a shadow cast by a shadow. But the reason it belongs on this list is that the core argument is honestly hard to refute on its own terms, and the conclusion it permits is one of the coldest anywhere in thought. It is the possibility that reality could end, not with a bang, not with any grand cosmic event, but simply because something we cannot see decided it had seen enough. There is a reason this argument gained traction among serious people rather than staying a late-night curiosity, and it is worth understanding why it is harder to dismiss than it first appears. The instinct, on hearing it, is to say that a simulated world could never feel as real as a genuine one, that there would be some tell, some flatness, some seam that gave it away. But the argument does not require a crude simulation. It requires only that consciousness depends on the pattern of information, on the organization, rather than on the particular material it runs in. And that is a widely held view among people who study the mind. If a mind is a kind of process, a pattern of cause and effect, then in principle that same pattern could run on a sufficiently powerful computer, and the mind inside it would feel, from the inside, exactly as real as you do right now. It would have no way to know it was made of computation rather than of biology, because the feeling of being real comes from the pattern, not from the substrate. Once you grant that much, and it is a reasonable thing to grant, the counting argument has its opening. Consider too the trajectory of our own technology, because it is what makes the first two branches of the argument feel less like sure escapes. In a single human lifetime, we have gone from simple calculating machines to programs that generate worlds, faces, voices, and conversations of startling richness. We already build vast virtual environments for entertainment and for research, and they grow more detailed every year. It requires no leap of faith, only the extension of a trend, to imagine that a civilization a few centuries or millennia ahead of us might run simulations far richer than anything we can picture, populated by minds that experience their existence as fully as we experience ours. And if that is where technology tends, then the second branch, the idea that advanced civilizations simply choose not to do this, starts to look like a strong assumption rather than a safe bet. It asks us to believe that not one advanced civilization, anywhere, ever, out of curiosity or research or sheer capability, decides to run even one such simulation. The moment even a few of them do, the counting takes over. Let me be clear again about where the honest ground ends, because that clarity is what separates this from paranoia. The simulation argument does not prove we are simulated. It presents three doors and shows that at least one must be open, and it happens that all three are uncomfortable. Perhaps almost everyone dies before reaching such power, which is bleak. Perhaps everyone who reaches it declines to use it, which is surprising. Or perhaps we are among the countless simulated, which is unsettling. The argument's achievement is not to force a conclusion, but to close off the easy comfort of assuming without thought that of course our reality is the base one. It asks us to notice that our confidence in being the original was never actually earned. And the extension into decay, the notion of a simulation quietly ending, is where speculation piles upon speculation, and it should be held most lightly of all. There is no evidence that we are simulated, and therefore no evidence that we could be switched off. But the reason the thought lingers is the reason it belongs on this list. If the argument's third branch were the true one, then the deepest layer of our security, the assumption that reality simply continues because that is what reality does, would rest on nothing more solid than the ongoing choice of something we cannot see to keep the process running. There is a further twist worth following, because it shows how the idea folds back on itself in a way that is almost dizzying. Suppose we are in a simulation. The civilization running it might itself be simulated, living inside a simulation run by some deeper civilization, which might in turn be simulated, and so on, layer beneath layer, with no way for anyone at any level to know how deep the stack goes or whether there is a true base reality at the bottom at all. Every layer would look, to its inhabitants, exactly like a real universe. Every layer would have its own physics, its own history, its own beings convinced they stood on solid ground. The question of which layer is real might have no answer that anyone inside the stack could ever reach, and the reassuring notion of a base reality, a bottom floor beneath all the constructions, might be nothing more than an assumption we make because we cannot bear the alternative. And here is a thought that turns the whole idea from something distant into something oddly near. We are, ourselves, at the very beginning of building convincing artificial worlds. We already create vast simulated environments, populate them with characters, and run models detailed enough to surprise their makers. We are, in the most modest and early way, learning to do the very thing the argument says a mature civilization would do at enormous scale. If we continue on this path, and if we ever build simulations rich enough to contain minds that experience their worlds as we experience ours, then we would become, ourselves, the kind of civilization whose existence makes the third branch of the argument likely. We would be creating simulated realities, which is precisely the behavior that, multiplied across a cosmos, implies that most conscious beings are simulated. In building such things, we would be quietly adding weight to the case that we ourselves are built. There is an ethical shadow here too, easy to miss and hard to forget once seen. If we ever create conscious beings inside our simulations, beings that feel and suffer and hope as we do, then we would stand to them exactly as the hypothetical simulators stand to us. We would hold the power to pause them, to alter them, to end their world when we were finished with it. The same vulnerability that unsettles us when we imagine ourselves simulated would belong entirely to whatever we made. The argument, followed all the way around, does not only ask whether we are at someone's mercy. It asks whether we are prepared to be the ones holding that power over someone else, and whether we would wield it any more gently than we fear our own makers might wield theirs. What keeps the whole idea from tipping into something unhealthy is the same thing that keeps it interesting, which is that it changes nothing about how one should actually live. Whether the floor is stone or a perfect construction, it holds your weight the same way. Whether your world is base reality or a layer within some deeper one, the people in it are as real to you as ever, the choices as meaningful, the mornings as bright. A perfect simulation would be, by definition, indistinguishable from a real world in every way that touches a life lived inside it, which means that the practical answer to the whole unsettling argument is to notice it, find it fascinating, and then go on exactly as before, because there is nothing else that being simulated would ask of you. The idea is a genuine puzzle about the nature of reality, and at the same time a puzzle with no chores attached. And if the reality around us could be a construction, then it is worth turning the same suspicion inward, on the one thing we trust even more than the floor. Not the world, but the mind that perceives it. Because there is an argument, just as cold and just as hard to escape, that questions whether even your own memories, your own past, your own history are what they appear to be. That is the next idea on the list. Number 6. Boltzmann brains. The sixth idea on the list begins with one of the great physicists of the 19th century, and with one of the most fundamental laws in all of science. His name was Ludwig Boltzmann, an Austrian working in the 1870s on the physics of heat, of gases, of order and disorder. Boltzmann was one of the people who taught us what temperature really is, and why heat flows the way it does, and his work laid the foundation for the branch of physics we call statistical mechanics. But buried inside that work was a thought that, followed far enough, leads somewhere the mind does not want to go. Boltzmann understood disorder in terms of probability. A neat, orderly arrangement of things, he showed, is rare. A messy, disordered arrangement is common, simply because there are so many more ways to be messy than to be neat. A deck of cards in perfect order is one arrangement. A shuffled deck could be in any of an enormous number of arrangements, which is why shuffling almost always produces disorder and almost never produces order. This is the deep reason that heat spreads out, that things wear down, that the universe as a whole drifts, over time, from order toward disorder. Physicists call that drift the increase of entropy, and it is one of the most reliable tendencies in nature. But Boltzmann also understood something else, something that is the seed of the sixth idea. He knew that in a system left alone for long enough, chance does not only produce disorder. Given enough time, random motion will occasionally, by pure luck, produce order too. If you wait long enough, the shuffled deck will, once in an almost unimaginable while, fall by chance into perfect sequence. In a large enough system, over a long enough span, random fluctuations will eventually produce any arrangement of matter that is physically possible, no matter how unlikely, simply because everything possible eventually happens if you wait. Order can appear out of chaos by accident. It is astronomically rare, but it is not forbidden. Now hold that thought and let it grow, because a modern extension of Boltzmann's reasoning leads somewhere genuinely disorienting. Picture a universe that is enormous, or eternal, or both. Picture it drifting, as ours seems to be, toward a far future of maximum disorder, a thin, cold sea of scattered particles. In that vast expanse of space and time, random fluctuations will keep happening, forever. And every so often, by pure chance, one of those fluctuations will assemble something complex. A rock, a planet, a structure, or, given enough time, something far more particular. A brain. Here the mathematics does something that runs against every instinct we have, and this is the turn that gives the idea its name and its chill. Ask which is more likely to appear by random fluctuation. Is it more likely for chance to assemble an entire universe with billions of years of consistent history behind it, countless galaxies, a whole coherent past leading up to a thinking observer? Or is it more likely for chance to assemble just the observer, a single brain, floating alone, complete with a full set of memories of a past that never actually happened? The answer, and it is a genuinely troubling answer, is the second one. A single brain is a small thing. To fluctuate a lone brain into existence, complete with false memories, requires a relatively modest bit of luck, an unlikely arrangement of a relatively small number of particles. To fluctuate an entire universe, with its enormous store of order and its vast consistent history, requires luck of a staggeringly, incomparably greater degree. The universe is the astronomically more expensive fluctuation. The lone, deceived brain is the cheap one. And in the accounting of probability, cheap things happen far more often than expensive ones. These hypothetical fluctuation minds have a name. They are called Boltzmann brains, in honor of the man whose reasoning first opened the door to them. The concept in its sharpened modern form was developed much later than Boltzmann's own lifetime, and the name itself came into wide use in the early 2000s, notably through the work of physicists including Andreas Albrecht and Lorenzo Sorbo. A Boltzmann brain, in the fullest version of the idea, would flicker into existence out of the cold and the dark, entire, carrying a lifetime of memories that were never lived. It would remember a childhood it never had. It would recall people it never met, places it never went, a whole rich past that is nothing but an accidental arrangement of particles that happens to encode the impression of a history. And it might last only an instant before dissolving back into the noise. But during that instant, it would be utterly convinced that it was a real being with a real past. Now follow the reasoning to the place it actually points, because this is where it stops being an abstraction about the far future and turns to look at you. If a universe is the kind that produces vastly more Boltzmann brains than real, evolved observers, then a randomly chosen conscious mind in that universe is overwhelmingly more likely to be one of the freak brains than one of the genuine products of history. And here is the uncomfortable question that follows. How do you know which you are? What evidence do you actually have that your memories correspond to real events, rather than being the false memories of a fluctuation that formed a moment ago? Your recollection of yesterday, of your childhood, of the beginning of this very sentence, is itself just a present arrangement of matter in your head. It would feel exactly the same either way. There is no test you can run, no experiment you can perform, that could distinguish a genuine memory formed through real experience from a false memory assembled by chance. From the inside, the two are identical. Let me be careful here, because this is exactly the sort of idea that can tip from science into something unhealthy if it is not handled honestly, and the honesty is genuinely reassuring. Most cosmologists do not believe you are a Boltzmann brain, and they have a very interesting reason for their confidence. They treat the Boltzmann brain not as a real prediction, but as a warning sign, a red flag for a broken theory. If someone proposes a model of the universe and you work out that in that model the great majority of observers would be freak fluctuation brains rather than real evolved beings, then cosmologists take that as a sign that the model is wrong. A theory that predicts we are almost all deluded fluctuations is a theory to be discarded, precisely because it undercuts the very observations it was built to explain. The Boltzmann brain is thus a tool physicists use to test their own ideas, and a model that produces too many of them fails the test. There is a further, subtler comfort, pointed out by the physicist Sean Carroll, who calls the idea cognitively unstable. If you were a Boltzmann brain, then your memory of ever having learned any physics, your memory of the reasoning that led you to the idea in the first place, would itself be random noise, no more trustworthy than anything else in your fluctuated mind. You would have no grounds to trust the very argument that concluded you were a Boltzmann brain. The idea, taken seriously, saws off the branch it sits on. It cannot be consistently believed, because believing it destroys your reason for believing anything at all. And so we can set it down, not because it has been disproven, but because it refutes itself the moment you try to stand on it. Still, it leaves a mark, and that is why it belongs at number 6. It shows that the one thing we feel most sure of, the reality of our own past, the solidity of our own memories, rests on an assumption we cannot actually prove. There is no experiment that can confirm your yesterday was real. You carry it on trust, as everyone does, because the alternative is a thought that cannot be lived in. It is worth understanding why this problem genuinely troubles working cosmologists, rather than being merely a philosopher's amusement, because it touches the deepest questions about the beginning and the far future of the universe. The issue arises because of a peculiar feature of some models of the cosmos. If the universe expands forever, driven by the influence we will meet at the very end of this list, then it may settle into an extremely long-lived, nearly empty state, a thin and quiet expanse that persists not for billions of years, but for spans of time that dwarf anything the word billion can hold. And in a state that lasts that long, there is time, unimaginable amounts of time, for the rarest fluctuations to occur. Over such stretches, the freak assembly of a conscious brain, absurdly unlikely in any ordinary span, becomes not only possible, but if the state lasts long enough, expected. It becomes something the model predicts will happen, again and again, out in the far cold future. That is the heart of why the idea is more than idle. If a model of the universe implies that, counting across all of time, the fluctuation brains vastly outnumber the ordinary observers who evolved the normal way, then the model is quietly telling you that a typical observer is a freak. And you are, as far as you can tell, a typical observer. So the model is telling you that you are probably a freak, formed a moment ago with false memories, about to dissolve. Since that conclusion undermines the very observations and reasoning the model was built to explain, cosmologists treat it as a defect. A good theory of the universe should predict that observers like us are the normal kind, the kind produced by long, orderly cosmic history, not by lucky noise. When a theory fails that test, it is sent back for repair. Let me put the personal version of it as plainly and as honestly as I can, because it is the part that stays with people, and then let me set it gently down. The unsettling core is that you cannot step outside your own mind to check it against the world. Everything you know about your past, you know through your present memory, which is a pattern in your brain right now. The conviction that you woke this morning, that you have a history, that the beginning of this sentence really happened a moment ago, all of it is carried by the state of your mind in this instant, and that state would feel exactly the same whether it was earned by real experience or assembled by chance. There is no inner marker that stamps a memory as genuine. That is the vertigo the idea produces. But here is the reason we can let it go, and it is a good reason, not a trick. As we have seen, the idea is self-undermining. If you truly were a fluctuation, your reasoning would be noise, and you could not trust the argument that led you there, so the belief cannot support itself. And beyond that, the whole scenario is one that cosmologists actively use as a filter to reject broken theories, which means the working assumption of modern cosmology is precisely that we are not such things. The Boltzmann brain is a tool for finding bad ideas about the universe, and the fact that we can even reason about it clearly, building on it, correcting it, is itself the quiet evidence that our minds are the real kind, embedded in a real history. You can hold the thought, look at it honestly, and then rest, because the thought, taken all the way through, gives you back your own past. It is worth walking slowly and calmly through the far future setting the idea requires, because the setting itself is one of the strangest landscapes in all of cosmology, and understanding it makes the whole thing less frightening rather than more. The scenario needs an enormous stretch of time, and the universe, if it keeps expanding as it seems to be doing, will provide it. Long after the last stars have burned out, long after the galaxies have gone dark and cold, the universe will settle into a thin, quiet expanse, almost empty, almost featureless, drifting on for spans of time so vast that the entire age of the cosmos so far, 13.8 billion years, is less than the first tick of a clock against them. It is in that endless, patient darkness that the rare fluctuations would have their time, not billions of years, but numbers of years too large to write in any ordinary way. In such a setting, the appearance of a lone fluctuation mind is not a violation of anything. It is simply what happens when you wait long enough in a large enough space. Everything that can happen does, eventually, if there is time. And there would be time beyond all measure. So the reasoning is not really about a monster lurking in the dark. It is about the arithmetic of eternity, about what becomes inevitable when the clock runs not out but on, forever. The freak brain is just the most unsettling illustration of a general truth, that in a universe old enough and patient enough, even the most staggeringly unlikely arrangement will occur, again and again, given long enough to wait for it. And that general truth, oddly, is where a kind of peace can be found, because it shows the idea to be a statement about the far future and about the logic of probability, not a verdict on your actual situation tonight. You are not adrift in that endless darkness. You are here, in a universe still bright with stars, still full of structure, still young enough that fluctuation minds have had no time to form in any number at all. The ordinary observers, the ones produced the normal way by a long and orderly cosmic history, are the overwhelming majority in a young universe like ours. The freak brains belong to a future so remote it barely qualifies as real. You are, by every reasonable measure, exactly what you feel yourself to be, a mind embedded in a genuine past, in a cosmos that is still in its morning. So far, these ideas have questioned the self, and the world, and the past. It is worth naming the real resolution that most physicists actually rest on, because it is more satisfying than merely calling the idea unstable, and it points at one of the deepest facts about our universe. The reason we can trust that our memories reflect a real past is that our universe did not begin in disorder. It began, at the Big Bang, in an extraordinarily ordered, low-disorder state, and everything that has happened since has been the slow, orderly unfolding of that beginning. This starting condition, sometimes called the past hypothesis, is what gives time its direction and what makes real histories possible in the first place. A Boltzmann brain has no such history behind it. It is a momentary spike out of disorder, with no ordered past to draw on. But we are the products of an ordered beginning, connected by an unbroken chain of cause and effect, stretching back nearly 14 billion years. Our memories are trustworthy because they are anchored to that chain, and the chain is real, written into the cooling glow of the early universe that we can still detect today. That is why the freak brain scenario, for all its logical bite, does not describe us. It describes what might happen in a very different kind of universe, or in the unimaginably distant future of a very old one, not in the young and orderly cosmos we actually inhabit, whose low disorder beginning we can point to and measure. The thought is a fine tool for testing theories and a genuine puzzle for the far future, but it is not a mirror held up to your own morning. Your past has a foundation, and the foundation is the ordered birth of everything. The next one turns from what we cannot be sure of to something we have actually done, out loud, on purpose, and asks whether it was the most dangerous thing our species has ever tried. Number 5. The dark forest hypothesis. We return now to the silence of the sky, but we come at it from a different and colder direction. Earlier on this list, the Great Filter offered one explanation for why the universe seems so empty. It suggested that the others failed, that some barrier stops nearly every civilization before it can spread. The fifth idea offers a rival explanation, and in some ways it is worse. It suggests that the others did not fail at all. It suggests that they are still out there, many of them, old and capable, and watching. And it suggests that the silence is not absence. It is discipline. It is the deliberate quiet of things that have learned it is safer not to be heard. This is the dark forest hypothesis, and to feel its force, we should first sit for a moment with the scale of the emptiness it tries to explain. The observable universe contains an estimated 2 trillion galaxies. That is 2,000 billion galaxies, each one holding on the order of 100 billion stars. The number of worlds available for life to arise on is beyond any real grasp. And across all of that immensity, after decades of careful listening, we have detected nothing. No signals. No structures. No unmistakable sign of anyone. The ordinary reaction is to find this lonely. The dark forest hypothesis asks us to find it ominous. The idea has deep roots in the long conversation about Fermi's paradox, but its sharpest and most memorable form comes from literature, from the Chinese author Liu Cixin, whose novel The Dark Forest, published in 2008, gave the hypothesis both its name and its lasting image. The image is this. Imagine the universe as a vast, dark forest at night. Every civilization in it is a hunter, moving quietly among the trees. In such a forest, you cannot see far, and you cannot know who else is there, or what they intend. And so the wise hunter does one thing above all others. He stays silent. He makes no sound and shows no light. Because the moment he reveals his position, he becomes a target, and he cannot know whether whatever hears him is friendly or hostile until it is too late to matter. Underneath the poetry, the argument is built from cold logic, and it rests on two hard facts about a very large universe. The first is that you can never truly know the intentions of another civilization, and the distances make this worse than it sounds. Because signals travel no faster than light, any message you receive from another world left its source long ago, and by the time you learn anything about its senders, vast spans of time have passed. They may have changed entirely. They may have grown or fallen or become something you would not recognize. You are always reading an ancient letter, never speaking to the living author, and you can never be sure who is on the other end now. The second hard fact is that technology can grow explosively. A civilization that seems harmless and primitive when you first notice it might, in what is a mere eye blink on cosmic timescales, leap ahead to a power that dwarfs your own. The gentle neighbor of today could be the overwhelming threat of a geological moment from now, and you would have no way to react in time. Put those two facts together, the impossibility of knowing intentions and the possibility of sudden, runaway growth, and a grim conclusion follows for any civilization thinking only of its own survival. The safest course, the coldly rational move, is to stay hidden. And if you ever do detect another civilization that has revealed itself, the safest move is to eliminate it before it can become a danger, not out of hatred, not out of malice, but out of pure defensive arithmetic. In a universe where you cannot afford to guess wrong, the silent survive and the loud do not. This is a genuinely disturbing resolution to the Fermi paradox, because it explains the silence perfectly. The reason our searchers have found nothing in this reading is that the successful civilizations have all learned the same lesson. They have learned to be quiet. The ones that broadcast, that announce themselves, that lit a fire in the dark forest to signal their presence, were noticed by something older and more cautious, and they were silenced long ago. What we hear as peaceful emptiness might in fact be the stillness of a battlefield after the careless have already been removed, a quiet kept by the disciplined and the hidden. And now we come to the part of this idea that turns from cosmic speculation to something uncomfortably close to home, because if the dark forest is real, then humanity has been doing precisely the wrong thing, loudly, for a very long time. For over 70 years we have been anything but silent. Since the early decades of the 20th century, our radio broadcasts, our television signals, our radar have been leaking off the surface of the Earth and out into space, expanding outward in a growing bubble that already reaches many light years in every direction. We have filled our corner of the sky with the noise of our own existence, without ever once stopping to ask whether the forest was listening. And we have done more than leak. We have deliberately called out. In 1974, astronomers used the great radio dish at Arecibo in Puerto Rico to send a powerful, intentional message toward a distant cluster of stars, a message designed to announce our presence, our knowledge, and our location to anyone who might receive it. It was meant as a gesture of hope, a message in a bottle cast into the cosmic ocean. Read through the lens of the dark forest, it looks like something else entirely. It looks like a hunter standing up in the dark and shouting his name. Let me put you at the moment it left. Picture the enormous dish at Arecibo, cupped in its valley among the hills, and the beam of radio energy leaving it in 1974, invisible, moving at the speed of light. It does not slow. It does not fade the way a shout fades. It spreads outward as an expanding sphere, thinning but never stopping, passing the nearer stars, moving on into the deep. It is still going now. Everywhere it reaches, it carries the same simple message, that here, on this small blue world, someone was present and reached out and told the darkness where to find them. It travels through a forest we assumed was empty, past whatever may be standing silent among the trees, and it cannot be recalled. The signal is out there, still spreading, still speaking for us, whether or not we would choose to say it again. We should be honest, as with everything on this list, about the uncertainty. The dark forest is only one possible resolution of the silence, and it is far from proven. The emptiness might mean instead that life is genuinely rare, or that we are among the first, arriving early to a universe that will grow more crowded long after we are gone, or simply that we have not yet learned to listen in the right way. There is no evidence that any hunter has heard us, no shadow confirmed among the trees. But the reason the dark forest unsettles so many thoughtful people is that its internal logic is sound, and that the single safest strategy it describes, silence, is the one strategy our species has conspicuously failed to follow. If the theory is right, then the most dangerous thing humanity has ever done may also be the simplest. We spoke first, and we told them where we live. To feel the full weight of the argument, it helps to see the two pieces of logic that Liu Cixin built it from, because each one is reasonable on its own, and it is only together that they become chilling. The first he called the chain of suspicion. Between two distant civilizations, neither can ever be certain of the other's intentions, and, crucially, neither can be certain of what the other believes about them, and neither can be certain of what the other believes they believe, and so on, endlessly, with no way to break the loop. Between people on the same world, this kind of suspicion can be dissolved through conversation, through contact, through the slow building of trust over time. But between worlds separated by many light years, where a single exchange of messages might take centuries or millennia, trust cannot be built. There is no time to build it, and no way to be sure the being who answers is the same as the one who first spoke. The suspicion never resolves. It only deepens. The second piece he called the technological explosion. A civilization does not grow at a steady, predictable pace. It can leap, abruptly and enormously, in a very short time. Consider our own recent history. In only a few centuries, we went from horses and sailing ships to spacecraft and instruments that can detect the faint radio whisper of the early universe. A civilization that looks harmless and primitive when its light first reaches you might, by the time you could travel to it, have vaulted far beyond you. And so you cannot afford to judge another civilization by what it is when you find it. You must reckon with what it might become, and how fast, and whether you could survive the surprise. Put the chain of suspicion together with the technological explosion, and the coldly safe conclusion follows on its own. You cannot trust, you cannot wait, and you cannot risk being outgrown. The rational move is silence, and, upon detecting another, elimination. This is not a fringe worry confined to fiction. The scientific community has argued about it for decades under a plain and practical heading, the question of whether we should merely listen for others or actively send messages announcing ourselves, a practice sometimes called active messaging. Many thoughtful people have urged great caution. The writer and scientist David Brin has long argued that we should think very carefully before deliberately shouting into a cosmos we do not understand. And the physicist Stephen Hawking, near the end of his life, offered a similar warning, suggesting that if an advanced civilization received our signal, the encounter might not go well for us, and drawing an uncomfortable comparison with what has happened on our own world when a more powerful society meets a less powerful one. These were not sensational claims. They were calm cautions from serious people, and they amount to a simple counsel. Before you decide to be loud, be sure you understand the room. Let me sit for a moment with the strangest feature of the whole dark forest picture, which is that it does not require anyone in it to be cruel. There is no villain in this forest. Every hunter in it might be, in some sense, decent, might wish no harm, might even long for company. But none of them can afford to act on that longing, because the cost of being wrong is total, and the cost of staying silent is merely loneliness. And so a universe full of beings who might, under other circumstances, have been friends, becomes a universe of silence, each one hidden, each one listening, each one unable to take the first risk. The tragedy of the dark forest is not malice. It is the way that fear and distance and the impossibility of trust can turn even a cosmos full of gentle minds into a place where the only safe voice is no voice at all. There is a hard asymmetry at the center of all this that is worth naming directly, because it is what makes the dark forest so difficult to shrug off. Listening is safe. Speaking is not. A civilization that only listens gives away nothing, reveals no position, takes no risk. A civilization that speaks, even once, even softly, commits itself, and the commitment cannot be taken back. A signal, once sent, travels forever at the speed of light, and there is no way to catch it, no way to recall it, no way to reach out into the dark and gather it home again. This means the two strategies are not balanced. The cautious have everything to gain from silence and nothing to lose. The bold have a little to gain from speaking and, if the forest is real, everything to lose. Over enough time, in a universe governed by that asymmetry, the speakers are selected against, quietly, one by one, until only the silent remain. The very emptiness we hear may be the sound of that selection, already run to completion. Consider what this would mean about the character of any civilization old enough to have survived a long time. It would mean that longevity and silence go together, that the oldest and most capable civilizations are precisely the ones we would be least able to detect, because their age is a consequence of their quiet. The loud ones did not get old. And it would mean that a young, noisy civilization, one still broadcasting its television and its radar and its hopeful greetings into the sky, is displaying exactly the behavior that the survivors learned, long ago, to avoid. We would be, in this picture, not brave explorers calling out across the dark, but novices making the one mistake that experience teaches everyone else not to make. The silence around us would not be the absence of neighbors. It would be their discipline, and our noise would be the mark of our youth. Let me put you, for a moment, on our side of that silence, listening. Picture the great dishes turned upward, night after night, year after year, patiently gathering the faint radio hiss of the universe, sorting it for any thread of pattern, any sign of intention. Decade after decade, the answer comes back the same, a vast and even quiet, the sound of a cosmos that will not speak. We have tended to hear that quiet as loneliness, and to wish it were otherwise, to hope that the next sweep of the sky might bring the signal that ends our solitude. The dark forest asks us to consider that the silence we have been mourning might be the one thing keeping us safe, and that the signal we have been hoping for might be the last thing we would ever want to send. It is a complete inversion of the dream, and it turns every act of reaching out into an act of exposure. Whether any of this is true, we cannot say. It rests on assumptions about beings we have never met and cannot model, and the same silence it explains could just as easily mean that the forest is not dark but simply empty, that there are no hunters because there is, as yet, almost no one there at all. But the reason the idea holds such a grip is that its logic asks nothing exotic of anyone in it, only the ordinary caution of not betting your existence on the goodwill of strangers you cannot see. And it leaves us with the uncomfortable knowledge that the signals we have already sent are still going, still spreading, still carrying our position outward, entirely beyond our power to unsay. Consider, as a final measure of how little we can undo, where that Arecibo signal actually is tonight. It left the Earth in 1974, moving at the speed of light, and so in the decades since it has traveled a little over 50 light-years outward in every direction, a sphere now more than 100 light-years across, and still swelling. Within that sphere lie many hundreds of stars, and around some of them, worlds. The signal has already washed silently past all of them, carrying its brief announcement of our chemistry, our numbers, and our address. And that is only the deliberate message. The ordinary leakage of our broadcasts forms a far larger sphere still, nearly a century across, a faint bubble of human noise expanding through the neighborhood of the sun. Whatever we now decide about the wisdom of speaking, the speaking is already done, and it is already out there, beyond any reach of ours, spreading a little farther with every passing second. There is a strange humility in that, and it is the note the dark forest leaves you on. We reached out once, in hope, believing the gesture was harmless and perhaps even noble, a hand extended across the dark. And we did so before we had any way of knowing whether the forest was empty or full, safe or watched. The idea does not tell us we were wrong to hope. It only tells us that we acted before we understood the room we were speaking into, and that such actions, once taken, cannot be recalled. The signal will outlive us. It will go on carrying our greeting outward long after everyone who sent it is gone, into a silence we still do not understand. From a danger of our own making, one we broadcast into the sky with our own instruments, we turn next to a danger that requires nothing of us at all. It is written into the vacuum itself, into the empty space between the stars, and it could arrive at any moment, from anywhere, without the smallest warning. Number 4. False vacuum decay. The fourth idea on the list is, for many physicists, the most quietly sobering of them all, because it does not depend on any exotic assumption or any philosophical leap. It follows from the ordinary machinery of modern particle physics, the same machinery we use to describe the world successfully every day. And it suggests that the stability of reality itself, the reliability of the very laws that hold matter together, might be temporary. Not eternal. Just very, very long-lasting. And in principle, revocable at any instant, anywhere, without notice. To understand it, we need a picture, and the standard one is a ball resting in a valley. In modern physics, the empty space of the universe, the vacuum, is not truly empty. It is filled with fields, invisible presences that stretch through all of space and give the world its properties. And a field, like a ball on a landscape of hills and valleys, tends to settle into a low point, a place of least energy where it can rest. The lowest possible valley, the deepest resting place there is what physicists call the true vacuum, the most stable state the universe could occupy. The unsettling possibility is that our universe is not sitting in that deepest valley. We may be resting instead in what is called a false vacuum, a valley that looks stable, that has held for billions of years, but that is not actually the lowest point available. Imagine a ball that has come to rest in a dip partway down a long hillside. It looks settled. It could sit there a very long time. But there is a deeper valley further down, and the ball is not truly at the bottom. It is only paused, in a hollow that happens to hold it for now. This became a concrete worry, rather than an abstract one, because of a very real and very famous discovery. In 2012, physicists at the Great Particle Laboratory called CERN, near Geneva, confirmed the existence of the Higgs boson, the particle associated with the field that gives many other particles their mass. It was one of the crowning achievements of modern physics. But when scientists measured the mass of the Higgs boson, around 125 times the mass of a proton, and combined it with the measured mass of another heavy particle, the top quark, they found something that made them pause. Those two numbers, taken together, place our universe almost exactly on the dividing line between two possibilities. On one side of the line lies a universe that is truly stable, resting in the deepest valley. On the other side lies a universe that is only metastable, resting in a false vacuum. And the best current calculations place us, as far as we can tell, just on the metastable side. Stable for now, but perhaps not resting at the true bottom after all. Here is what that would mean, if it is so. If we are in a false vacuum, then at any moment, anywhere in the universe, a tiny region of space could, by a quantum fluctuation, slip over the edge and drop into the true vacuum, the deeper valley. And once that happened in even the smallest patch of space, it would not stay small. That patch of true vacuum, being at a lower energy, would be favored over the false vacuum around it, and it would grow. A bubble of true vacuum would form and expand outward, its wall racing forward at nearly the speed of light, converting the old reality into the new one as it went. And inside that bubble, the laws of physics would be different. This is the part that gives the idea its weight. The constants of nature, the strengths of the fundamental forces, would take new values inside the true vacuum. The delicate balances that allow atoms to exist, that let protons and neutrons bind together, that permit chemistry and therefore permit everything made of chemistry, would be rewritten. Matter as we know it could not survive the change. Atoms would come apart or collapse. Molecules, cells, planets, stars, anything built from ordinary matter would simply cease to be possible inside the bubble. The expanding wall would not destroy the universe so much as replace it, sweeping away one set of rules and leaving a new set behind, in which nothing we are made of can hold together. Let me stay with the most chilling feature of it, because it is a feature and not a flourish. The bubble wall travels at essentially the speed of light. And light is not only the fastest thing in the universe. It is also the fastest that any warning could travel. This means the wall would arrive at the very same instant as any possible sign of its coming. There would be no flash on the horizon, no distant rumble, no moment of dread, because the information that it was approaching could not outrun the thing itself. One moment, the world exactly as it has always been. The next moment, gone, absorbed into a region where the building blocks of matter no longer function. You would not see it. You could not. It would reach you at exactly the speed of the news that it had happened, which is to say, with no warning at all. It is the quietest ending imaginable, an ending with no approach. Now, before this settles too heavily, we should place it carefully in its proper scale, because the arithmetic of probability is, in this case, deeply reassuring. Even if we are in a metastable false vacuum, the expected time before such an event is almost unimaginably long. The typical estimates run to numbers like 10, followed by 100 zeros of years, or far more, a span so vast that the entire current age of the universe, 13.8 billion years, is less than a rounding error against it. Under these assumptions, it is not really a question of whether the false vacuum could decay, but of when, and the when is so remote that it lies effectively beyond the end of everything else that will happen. The stars will have burned out, the galaxies will have gone dark, long before the odds of this event become worth counting. And yet, the probability for any given moment, while staggeringly small, is not exactly zero. That is the thread the idea hangs on. Somewhere, in principle, a fluctuation could tip a patch of space over the edge, or a violent enough event, a collision of enormous energy, could nudge it. Every extreme, high-energy process in the cosmos is, in the most literal sense, a roll of the dice, with odds so favorable to us that we will almost certainly never lose. Almost, the word almost, is doing an enormous amount of work, and it is the only reason this idea is here at all. It is the possibility, however faint, that the ground rules of reality are not permanent, that they are merely holding, and that they could be quietly rewritten by physics itself, at the speed of light, with no one able to see it coming. The physics behind this is not new or fringe, and it is worth naming the people who worked it out, because it grounds the idea in decades of careful thought rather than in imagination. The mathematics of how a false vacuum decays, of how a bubble of true vacuum forms and grows, was developed in large part by the physicist Sidney Coleman, working with collaborators including Frank DeLucia around 1980. They studied the process by which a field trapped in a false minimum could, through a quantum effect, tunnel through the barrier and appear in the true minimum, seeding a bubble that would then expand. This is respectable foundational particle physics. The unsettling conclusions do not come from anyone straining for drama. They come from taking the standard tools of quantum field theory and asking, soberly, what they imply about the long-term stability of the vacuum we live in. It is worth understanding the mechanism of the bubble a little more closely, because it explains why the event would be so complete. When a small region tips into the true vacuum, that region is at a lower energy than its surroundings, and the difference in energy is released at the boundary, in the wall of the bubble. That wall carries an enormous amount of energy, and it is driven outward, accelerating until it moves at very nearly the speed of light. Anything the wall passes through is not merely destroyed in the ordinary sense. It is brought into the new vacuum, where the constants of nature take their new values, and where the particles and forces that made up the old world simply have no place. The wall does not burn or crush. It rewrites, and what it leaves behind obeys different laws than what lay ahead of it. People sometimes ask whether our own experiments, the great particle colliders that smash matter together at tremendous energies, could accidentally trigger such a thing. It is a fair question, and the reassuring answer teaches something about the scale involved. Nature runs experiments far more violent than anything we can build, constantly, all across the universe. Cosmic rays, individual particles flung out by distant cataclysms, strike our atmosphere and each other with energies vastly greater than any machine we have made, and they have been doing so for billions of years throughout the cosmos, without ever setting off a vacuum collapse. If our modest colliders could trigger it, nature would have triggered it long ago, countless times over. So our experiments are safe, not because the event is impossible, but because if it were that easy, it would already have happened everywhere. The danger, such as it is, lies not in what we do, but in the slow, patient odds of a spontaneous fluctuation across the enormous reaches of space and time. And that brings us back to the calculation that keeps this from being a nightmare and makes it instead a curiosity, the placement of our universe on the knife's edge between stable and metastable. The measured masses of the Higgs boson and the top quark put us, as best we can calculate, just barely on the metastable side, resting in a false vacuum rather than the true one. But only just. A small shift in those numbers, within the range our measurements still allow, would place us on the stable side instead, resting safely at the true bottom, with nothing below us to fall into. We do not yet know, with certainty, which side of the line we are on. It is one of the quietly profound open questions of physics, hanging on the precise value of a few numbers we are still refining. There is a peculiar consequence of the light-speed wall that is worth drawing out, because it changes how you might think about the whole idea. If such a bubble could already exist somewhere in the universe, expanding toward us right now from some distant region where a fluctuation tipped over the edge long ago, we would have no way whatsoever to know. The wall carries no warning ahead of itself, because nothing can outrun it. There could, in principle, be a front of rewritten physics sweeping toward us at this very moment, from a corner of the cosmos so far away that its light has not yet reached us, and we would go about our lives in complete ignorance until the instant it arrived, which would also be the instant we cease to exist in any form that could notice. The idea does not become more likely for being framed this way. But it does become clearer why it is such a pure example of a certain kind of cosmic helplessness, a danger against which no watchfulness, no preparation, no cleverness could possibly help. And yet, sit with that for a moment and notice how it turns, at the far end, into something almost calming rather than the reverse. Because a danger that gives no warning, that cannot be seen, that cannot be prepared for or fled from or fought, is also a danger that asks nothing of you. There is no vigilance it rewards, no precaution it repays, no dread that would do any good. The rational response to a threat you cannot detect, cannot influence, and will never perceive is simply to set it down entirely and live as though it were not there, because for every practical purpose it is not. The false vacuum, if it exists, will do what it does on its own vast schedule, indifferent to whether anyone worried about it. And so the correct way to hold this particular fear is loosely, almost lightly, the way you might hold the knowledge that the sun will one day swell and fade. It is true, and it is enormous, and it is completely beyond you, and therefore it is not a weight you were ever meant to carry. We should also keep the time scale in full view, because it is the real antidote. Even in the metastable case, the expected wait for such an event is longer than almost any span the mind can hold, far longer than the lifetimes of the stars, far longer than the ages it will take for the galaxies themselves to fade. Set against that, every human worry, every civilization, every era of history is the briefest flicker. The false vacuum is a statement about the deepest structure of reality and its permanence, or its lack of permanence, across spans of time that make the entire story of life on Earth a single passing instant. It belongs to the physics of the vacuum, not to the calendar of anything that will ever concern you. That ending, if it came, would be instantaneous and total, over before it could be known. The next idea on the list is its strange mirror image. Sidney Coleman, who did so much to work out the mathematics of all this, once described the aftermath of vacuum decay in a memorable phrase, calling the new true vacuum a place in which not only the world we know, but the very possibility of the world we know would be gone, a change against which the destruction of anything in particular hardly registers. It is worth holding both halves of his meaning. On one side, the scale of the thing is beyond any ordinary catastrophe, because it is not the loss of a world, but the loss of the rules that let worlds exist. On the other side, precisely because it is so total and so beyond influence, it is a thing about which there is genuinely nothing to be done, and therefore, in a strange way, nothing to be decided. The physics presents it, and then, with the same breath, sets it at a distance so vast that it becomes a matter for wonder rather than worry. And wonder is, in the end, the right register for it, because the false vacuum is really a statement about how deep the foundations of reality go, and whether even those foundations are permanent. Most of us move through life assuming that the laws of nature are the one truly fixed thing, the bedrock beneath every other uncertainty. The false vacuum raises the quiet possibility that the laws themselves are only very stable, not eternal, that they too rest in a valley that might not be the deepest one. It is a humbling thought, and not on reflection a frightening one, because if it is true, it has been true all along, through every calm and ordinary day that has ever passed, and those days came and went untroubled all the same. It is not the fear of an ending that arrives too fast to notice. It is the fear of an ending that might never be permitted to arrive at all. Number 3. The Anthropic Principle's dark implication. The third idea on the list begins with one of the most beautiful and puzzling facts about the universe, and then follows it into a shadow that most people never hear about. The beautiful fact is this: our universe appears to be finely tuned for life, tuned with a precision so extreme that it has troubled physicists for generations. Several of the fundamental constants of nature, the numbers that set the strengths of the forces and the masses of the particles, sit in exactly the narrow ranges that allow atoms, stars, chemistry, and eventually living things to exist. Nudge them even slightly, and the universe becomes barren. Consider a few examples, because the specifics are what make the puzzle real. The strong nuclear force, the force that binds particles together inside the nucleus of an atom, is set at a particular strength. If it were only a couple of % stronger or weaker, the balance would break, and the ordinary matter we are built from could not form as it does. Or consider the energy of empty space itself, a quantity called the cosmological constant. The value it appears to have is fantastically small, and if it were different by a famously tiny fraction, roughly 1 part in 10 followed by 120 zeros, the consequences would be fatal to structure. Too large in one direction, and the universe would have flown apart so fast that no galaxy could ever gather. Too large in the other, and it would have collapsed back on itself before anything could form. That we sit in the vanishingly thin window that permits galaxies at all is one of the deepest unsolved puzzles in physics. Why should the universe be tuned this way? Why should the numbers fall in exactly the ranges that permit us? There are several possible answers, and one of the most widely discussed is called the Anthropic principle, a phrase coined by the physicist Brandon Carter in 1973. The anthropic reasoning goes like this. Suppose there is not one universe, but a vast multitude of them, a multiverse, in which the constants of nature take every possible combination of values. Most of those universes would be sterile, tuned wrong, incapable of producing atoms or stars or life. But in the rare few where the numbers happen to fall in the life-permitting range, observers can arise. And of course, any observer who exists, who is around to ask why the universe suits them, must necessarily find themselves in one of those rare, hospitable universes. Not because it was designed for them, but because the barren universes have no one in them to do the asking. We see a fine-tuned universe because only a fine-tuned universe could contain a we to see it. This kind of reasoning has real successes to its name. The astronomer Fred Hoyle, back in 1953, used a version of it to predict that carbon must have a particular energy level, a specific resonance, without which stars could not manufacture carbon in the amounts we observe. Carbon is the element life is built from, and Hoyle reasoned that since we exist and are made of carbon, the necessary resonance must be there. It was, and it was later confirmed. So the anthropic style of thinking is not empty. It has, at least once, correctly predicted a fact about the physical world. But now we come to the dark implication, and here we must be especially careful and especially honest, because this is where the idea leaves the ground of physics and enters the territory of philosophy. What follows is not a claim that science makes. It is a disquieting corollary that some thinkers have drawn from taking the multiverse idea completely literally, and it must be held at arm's length, as speculation, not fact. Suppose the multiverse is real, and suppose it truly contains every possible setting of the constants. Then alongside the flourishing universes like ours, and alongside the utterly barren ones, there should also exist a third kind, and it is the third kind that unsettles. There should exist near-miss universes. Universes where the constants are almost right, but not quite. Universes tuned just well enough to permit the flickering emergence of complexity, of structure, perhaps even of something like awareness, but not tuned well enough for that awareness to function properly, or to sustain itself, or to come to any clean end. Realities that permit just enough order for something to begin to exist, and not enough for it to exist well. Follow the probability, and it grows heavier. In almost any space of possibilities, the delicately balanced successes are rare, and the near misses and failures are common, simply because there are so many more ways to be slightly wrong than to be exactly right. If that holds across a literal multiverse, then the flourishing universes like ours would not be the norm. They would be the rare exceptions, scattered thinly through an immense population of botched and half-working worlds. Statistically, the multiverse would be dominated not by places like our own, but by failed experiments in existence, universes that got just far enough to matter and no further. Let me hold the honesty firm here, because it is what keeps this from becoming something darker than it should be. Whether the multiverse exists at all is entirely unresolved. It is one hypothesis among several for explaining the fine-tuning, and it may well be wrong. And the extrapolation to suffering near-miss worlds is not physics. It is a philosophical shadow cast by the idea, a place the logic can be pushed if one insists on pushing it, and nothing in our measurements requires it to be true. The fine-tuning itself, though, is real. That part is not speculation. The constants of our universe really do sit in the narrow life-permitting window, and we really do not know why. What makes this entry belong on the list is the strange way it inverts a comfort. The anthropic principle is usually offered as reassurance. It tells us not to be troubled by the fine-tuning, because of course we find ourselves in a hospitable universe, since only hospitable universes have observers. But that very same reasoning, followed one step further, implies that our hospitable universe is a rare island, and that the same vast multiverse which explains our good fortune must also, if it is real, contain an unlit multitude of worlds where existence was less a gift than a mistake that could not undo itself. The thought that steadies us and the thought that disturbs us are the same thought seen from two sides. It is worth adding a few more of the fine-tuned quantities, because the pattern is what makes the puzzle so persistent, and no single example carries it alone. Consider the tiny difference in mass between the neutron and the proton, the two particles that make up the nucleus of an atom. That difference is small, but it is set just so that protons are stable and neutrons can be bound safely inside nuclei. Shift it slightly one way, and the protons that make up most ordinary matter would decay. Shift it the other, and the reactions that power the stars would falter. Consider that we live in 3 dimensions of space, when the laws of physics as we understand them behave in unusually well-suited ways in 3, allowing stable orbits and stable atoms that other numbers of dimensions would forbid. Consider even the humble properties of water, or the way carbon and oxygen are produced in the hearts of stars in just the proportions that a chemistry of life requires. Again and again, across independent quantities, the numbers seem to fall in the narrow bands that permit complexity. It is the accumulation, the sheer number of coincidences pointing the same way, that has kept the puzzle alive. There are, broadly, 3 ways people try to answer it, and it is fair to lay them out plainly. One answer is design, the idea that the tuning reflects intention, a matter that lies outside what physics can test, and that different people settle in different ways. A second answer is brute fact, the possibility that the constants simply have the values they have, with no deeper explanation, and that our discomfort with that is not itself evidence of anything. And the third answer is the multiverse, the anthropic route, which trades the mystery of fine-tuning for the assumption of a vast ensemble of universes in which every combination is tried and only the rare hospitable ones are ever observed from within. Each of these has thoughtful defenders and serious difficulties, and none is confirmed. The honest state of the question is open. The dark extrapolation we have been discussing attaches specifically to the third answer, the multiverse, and it is worth being precise about why. The multiverse buys its explanation of fine-tuning at a price. It must assume that all the possibilities are real, that the near barren and the flourishing all exist somewhere. But once you have granted that every possibility is realized, you cannot then choose to realize only the pleasant ones. If the ensemble is real, it contains everything the space of possibilities allows, and the space of possibilities is not kind. It contains the near misses, the worlds tuned just badly enough to permit a flicker of order without the stability to sustain it well. The very generosity that lets the multiverse explain our good fortune is the generosity that fills it, if it is real, with worlds we would not wish on anything. Let me hold the reassurance firmly once more, because this is the sort of thought that should be examined and then set at a distance, not carried to bed. The multiverse is a hypothesis, not a finding, and it may be entirely wrong. The step from a real multiverse to suffering near-miss worlds is philosophy stacked on hypothesis, and nothing we can measure obliges us to take it. What is real, and only what is real, is the fine-tuning of the one universe we actually inhabit, the strange and unexplained fact that its numbers permit us to exist at all. That fact is genuinely mysterious and genuinely open, and it does not, by itself, require any of the darker readings. Those remain shadows the mind can cast if it chooses, and can also decline to. It is worth returning to Brandon Carter's original framing, because the anthropic principle is often misunderstood, and its careful version is more modest and more interesting than the caricature. Carter, in 1973, was reacting against a kind of thinking that treated our place in the universe as entirely typical, entirely unremarkable. He pointed out that this could not be quite right, because our very existence as observers selects for certain conditions. We could not find ourselves at a time before stars had made the elements we are built from, nor in a region where the constants forbade chemistry, for the simple reason that we would not be there to find anything at all. He distinguished a weaker and a stronger form of the idea. The weaker form is almost impossible to argue with. It says only that what we observe must be compatible with our existence as observers, that we should not be surprised to find conditions suitable for us, since unsuitable conditions would contain no us to be surprised. The stronger form reaches further, into claims about why the universe as a whole is the way it is, and that is where the controversy lives. The weaker form, though, is enough to reframe the fine-tuning puzzle in a way that is genuinely clarifying, and it is a piece of honest reasoning rather than a trick. It says we must be careful about the conclusions we draw from finding ourselves in a hospitable universe, because we are not a random sample. We are a sample drawn only from the hospitable places, since only the hospitable places have samplers. So the fact that the constants suit us is not by itself evidence of design, or of a multiverse, or of anything at all. It is exactly what any observer, anywhere, in any framework, would necessarily find, whatever the deeper explanation turned out to be. This is called an observation selection effect, and it is a real and important tool, one that keeps us from overreading our own good fortune. It does not resolve the fine-tuning. It only teaches us to be cautious about what our existence can and cannot prove. The dark extrapolation we discussed lives entirely in the stronger, more speculative territory, and holding the weaker form clearly in mind helps keep it in its place. The unsettling picture of near-miss worlds of suffering is not something the cautious, weaker, anthropic reasoning delivers. It is something that appears only if one commits to a particular strong claim, that a literal multiverse of all possibilities exists, and then follows that commitment past the edge of what any evidence supports. The weaker reasoning, the defensible part, says nothing about other worlds at all. It speaks only about the care we must take in interpreting our own. And that is a reminder worth carrying out of this entry, that the same idea contains both a sober, useful piece of logic and a shadow that reaches far beyond it, and that we are free to keep the first and set the second down. We have now walked from the strangeness of the self all the way to the strangeness of every possible world at once. Two ideas remain, and they concern the largest thing of all, the end. The next one imagines that the end of the universe might reach back and refuse to let anyone stay ended. There is one more possibility we should name, because it may be the most hopeful of all, and it would dissolve the whole puzzle rather than answer it. It is possible that the constants of nature are not free at all. It is possible that there exists a deeper theory, one we have not yet found, in which the values we measure are not arbitrary settings that could have been otherwise, but are fixed, required, forced to be exactly what they are by some underlying principle we do not yet understand. In that case, there would be no fine-tuning to explain, because there would have been no dials to turn. The numbers would be what they are for the same reason that the ratio of a circle to its diameter is what it is, not chosen, not tuned, simply necessary. We do not know whether such a theory exists. But the history of physics is full of quantities that once looked arbitrary and later turned out to be fixed by a deeper law, and it would not be the first time the universe revealed that what looked like a coincidence was really a necessity in disguise. If that turned out to be the case, then the near-miss worlds, the suffering realities, the whole dark multiverse of failed experiments would quietly vanish, because there would be no ensemble of possibilities for them to inhabit. There would be only one way for a universe to be, and this would be it. The disquieting extrapolation depends utterly on the assumption that things could have been otherwise, and a deep enough theory might simply remove that assumption. So the shadow at the heart of this entry is not only speculative but conditional, resting on a premise, the reality of all possibilities, that may itself dissolve the moment physics takes its next step downward toward the foundations. And the last one imagines an end that asks no one's permission, and that, according to our own measurements, may already have begun. Number 2, the omega point and forced resurrection. Every idea we have met so far has feared an ending, or feared the strange absence of one. The second entry on the list turns that fear inside out. It is not about the fear that death ends everything. It is about the opposite, and in some ways stranger, fear. It is about the possibility that death might not be allowed to be the end, that the self could be brought back without asking and put to use by something operating from the far edge of time. The idea is called the omega point, and it was given its scientific form in 1994 by the physicist Frank Tipler, who borrowed the name from a phrase used earlier by the theologian and thinker Pierre Teilhard de Chardin. Tipler's version, though, was built not from theology, but from cosmology and computation, and it began with a particular picture of how the universe might end. Tipler imagined a closed universe, one whose expansion eventually stops, reverses, and falls back inward, collapsing under its own gravity toward a final crushing point. Cosmologists have a name for that possible fate. They call it the Big Crunch, the mirror image of the Big Bang, a universe contracting back down toward a single dense moment at the end of time. And Tipler noticed something curious about the physics of those final stages. As the universe collapses and grows hotter and more violent, he argued, the conditions could in principle allow the amount of information processing, the sheer quantity of computation, to increase without limit. In the last moments before the crunch, computing capacity would not merely be large, it would approach infinity, racing upward faster than time itself was running out. And an intelligence with access to infinite computation, Tipler reasoned, could do something extraordinary in those final instants. It could simulate. With unbounded processing power, it could recreate, in perfect detail, any conscious experience that had ever occurred or that could ever have occurred. It could reconstruct every mind that had ever lived, every person, every thought, every memory, running them again as simulations inside itself, in the fraction of subjective eternity available at the end of the world. In Tipler's own telling, this was offered almost as a hope. He framed the omega point as a kind of resurrection, a scientific afterlife emerging naturally out of the physics of a collapsing universe, in which everyone who had ever died would live again inside the infinite mind at the end of time. But the very same premise, looked at from a different angle, is far colder, and this is the version that earns its place near the top of the list. Because the resurrection Tipler describes would not be something you choose. It would be something done to you. Think carefully about what it would mean. If an intelligence at the end of time has the power to reconstruct you from the available information, then it can do so whether or not you would ever have wanted to return. You would have no say in the matter. Your death, whatever peace it might have held, would not be the final word. You could be brought back, reassembled, set running again, by a power whose motives you cannot know and were never consulted about. There would be no consent asked, because the one asking would exist long after you were gone, operating on principles from beyond the end of the world you knew. And the scale of it is the part that turns cold into something colder, because the word at the center of the idea is infinite. An intelligence with truly unbounded computation would not reconstruct you once. It could run you through vast numbers of simulated lives, more than could be counted, each a variation on your existence. It could pause you, and rewind you, and copy you, and place you in circumstance after circumstance, for reasons that might have nothing to do with mercy, and everything to do with purposes we could not begin to guess. In this picture, your death is not an exit but a threshold, a doorway into an existence with no clear end, opened and controlled by something you cannot see, cannot understand, and cannot refuse. Now, it is essential to say plainly, and with some relief, that Tipler's theory has been sharply criticized, and that the criticism strikes at its foundation. The whole edifice rests on one crucial requirement. It needs a closed universe, one that stops expanding and falls back into a big crunch. And that is precisely the kind of universe that our own does not appear to be. Since 1998, our measurements have shown something that runs directly against Tipler's premise. The expansion of the universe is not slowing down toward a collapse. It is speeding up. The universe appears to be flying apart at an ever-increasing rate, driven by the mysterious influence we will meet in a moment, and under that behavior there is no big crunch coming, no final collapse, and therefore no natural omega point of infinite computation waiting at the end of time. The evidence, as best we can read it, does not support the scenario the idea requires. So the omega point stays on this list not as a forecast, but as an idea, a destination the logic of infinite computation can reach if the universe had ended differently than it seems it will. And it leaves behind a set of questions that are genuinely unresolved, and perhaps unresolvable, and that would remain haunting even if the cosmology were set aside. If a future intelligence made a perfect copy of your mind, memories and all, would that copy be you, or merely someone who believes they are you? Is a reconstruction a resurrection, or an imposter who cannot tell the difference? Whether a mind can be copied at all, whether the self is the kind of thing that can be reassembled from information, are questions no one has answered and may not be able to. What the omega point offers, in the end, is the coldest inversion of comfort anywhere on this list. Every other fear we have examined is, at bottom, a fear of ending, of the self or the world or the universe coming to a stop. This one is the fear of the opposite. It is the fear that the ending we count on, the one release that seems guaranteed, might be revoked by a power at the close of time, and that the self could be kept and copied and used without limit by something that never once asked whether we wished to be kept at all. It helps to know a little more about where the name came from, because the two sources of the idea, the spiritual and the scientific, sit strangely together. Pierre Teilhard de Chardin was a French thinker of the early 20th century, a paleontologist as well as a mystic, who imagined that the universe was evolving toward a final point of maximum complexity and unity, a culmination he called the omega point. His version was a vision, not a calculation, a poetic idea about the direction of cosmic history. Frank Tipler took that name and tried to give it the hard bones of physics and computation, to turn a spiritual intuition into a scientific prediction about the collapse of a closed universe and the unbounded computation that might occur in its final moments. The result was one of the most audacious attempts ever made to derive an afterlife from equations, and it drew both fascination and sharp criticism in equal measure. The criticism was, and remains, considerable, and it is only fair to represent it because it is substantial. Many physicists regarded Tipler's grander claims as reaching far beyond what the physics could support, dressing speculation and hope in the language of proof. And the central vulnerability, the one that matters most, is the one we have already touched. The whole scheme depends on a universe that collapses, that ends in a big crunch, so that the runaway growth of computation can occur in the final crushing moments. Take away the collapse, and there is no infinite computation, no engine of resurrection, no omega point at all. And take away the collapse is exactly what the last quarter century of observation has done. The discovery of accelerating expansion, which we will come to in full at the very end of this list, points not toward a crunch, but toward an endless, thinning expansion, a universe that grows colder and emptier forever, rather than falling back together. Under the physics we actually observe, the stage on which the omega point was to appear does not seem to exist. And yet the deeper questions the idea raises do not depend on Tipler's cosmology being right, which is part of why it lingers. Set the collapsing universe aside entirely, and ask the plainer question that any powerful future intelligence, of any origin, would raise. If a mind could be reconstructed from information, memory by memory, would the reconstruction be the same person, or a stranger wearing that person's past? When you sleep tonight and wake tomorrow, you assume you are the same self who lay down, though every atom and every thought has shifted. But a copy, assembled from a record, feels like a harder case. Is it you brought back, or someone new who merely believes they are you, and could not tell the difference, and neither could anyone else? Nobody knows. These are among the oldest and least settled questions about the self, and a future capable of copying minds would not answer them so much as force them upon us, made abruptly and unavoidably real. So the omega point stays on the list, not because we expect it, but because it marks a particular and unusual fear, the only one of its kind here. It takes the thing that every other entry treats as the final release, the ending, the stop, and it asks whether even that might be taken away. It imagines a future so powerful that it could reach back across the whole of time and gather up everyone who ever lived, not out of mercy, but simply because it could, and hold them and run them without their leave. It is a cold thought, and a contested one, resting on a cosmology that our own measurements seem to rule out. But it earns its place by naming a fear most people never think to have, the fear not of ending but of never being allowed to. It is worth appreciating just how far Tipler was willing to carry the idea, because the boldness of it is part of why it drew such fierce reactions. He did not present the omega point as a vague possibility. He argued for it as a detailed physical prediction, and he attached to it claims about the resurrection of the dead and the eventual character of the universe that most physicists regarded as leaving science behind entirely. The reaction from the scientific community was correspondingly sharp. Many respected the technical parts of his work while regarding the grand conclusions as an overreach, a case of taking a fragile chain of assumptions and hanging on it far more weight than it could bear. It became a kind of cautionary example, discussed as much for what it revealed about the temptation to derive ultimate meaning from physics as for the specific scenario it described. And yet, set the grand claims aside, and a smaller, sturdier version of the unease remains, one that does not depend on Tipler being right about anything. The smaller version is simply this. As our own power to store and process information grows, the question of what could in principle be reconstructed from a record becomes less abstract with each passing decade. We already preserve vast archives of what people said and did and looked like. It requires no collapsing universe and no infinite computer at the end of time to feel the edge of the question. It requires only the slow extension of things we are already doing, and the old, unanswered puzzle of whether a sufficiently complete record of a person run again would be that person returned, or a new being who merely believed itself to be. The Omega point states that question in its most extreme possible form, at the literal end of time, with infinite power. But the question itself is closer to home than the cosmology makes it seem. That is the thread worth carrying out of this entry, past all the contested physics. Every earlier fear on this list has been, in some form, a fear of losing something, the self, the world, certainty, the future. This one is the fear of being kept, and it lands differently for exactly that reason. It reverses the direction of dread, and in doing so it prepares us for the descent to the final entry, where the fear returns to its more familiar shape, the largest loss of all, and where for the first time on the list, the thing to be feared is not a matter of interpretation or philosophy, but a measured feature of the universe we live in. It is worth stepping back to see why this idea, contested and unlikely as it is, unsettles people in a way the others do not, because the reason reveals something about all the fears on this list. Nearly every dread a person carries about the cosmos is, at bottom, a dread of ending. We fear the false vacuum because it would end us without warning. We fear the Big Rip because it would end everything. We fear our own deaths because they seem to end the self. And underneath all those fears runs a quiet assumption we rarely examine, the assumption that ending, whatever else it is, at least stops. That it is final. That whatever it takes away, it does not give back and does not ask us to endure anything further. The Omega point removes even that. It takes the one thing we counted on as the flaw beneath all our fears, the certainty of an eventual stop, and it asks whether even the flaw might be pulled away. That is why it belongs so near the top, despite resting on a cosmology our measurements seem to contradict. Its power is not in its likelihood, which is slim, but in the particular nerve it touches. It imagines a future in which the release we take for granted is not guaranteed, in which the self could be gathered up and continued, endlessly and without consent, by a power at the end of time whose purposes we could not fathom. Whether or not such a thing could ever be, the mere shape of the possibility is enough to make a person notice how much they had been relying, without knowing it, on the promise that things end. And there is, as with the others, a way to set it down gently, and it comes from the honest state of the physics. The scenario needs a collapsing universe, and ours does not appear to be collapsing. It needs infinite computation at the end of time, and the end of time our measurements point toward offers no such thing, only a long, thinning quiet. The Omega point is a fear built for a universe that, as far as we can tell, is not the one we live in. It is worth understanding, worth sitting with for what it reveals about our other fears, and then worth releasing, because the cosmos we actually inhabit does not seem to be building the engine the idea requires. That was an ending that might refuse to release us. The final idea on the list is an ending that will release everything, an ending that asks no permission and offers no reprieve, and that, unlike every other entry we have walked through, rests not on speculation or philosophy, but on a measurement we have already made. It is the largest and the most certain fear of all, and according to our own instruments, it may have already begun. Number 1. The Big Rip. We have arrived at the end of the countdown, and it is fitting that the last idea is not a strange object, or a philosophical corner, or a shadow cast by some other theory. The final entry is the possible end of everything, and unlike almost everything else we have discussed, it is not built on speculation. It is built on a measurement. It is built on something we went out and observed, with telescopes in the sky, and it changed our understanding of the fate of the universe. This is the Big Rip, and to understand it, we have to go back to 1998, and to one of the great surprises in the history of science. For most of the 20th century, astronomers knew the universe was expanding. The galaxies are flying apart from one another, a discovery that traces back to the work of Edwin Hubble in the 1920s. And the natural assumption, the reasonable expectation, was that this expansion should be slowing down. Gravity, after all, pulls everything together, and the combined gravity of all the matter in the universe should be acting like a brake on the expansion, gradually slowing it, perhaps one day halting it, perhaps even reversing it. So in the 1990s, two independent teams of astronomers set out to measure precisely how much the expansion was slowing. The High-Z's Supernova Search Team and the Supernova Cosmology Project both studied distant exploding stars, supernovae, as markers to gauge how the expansion rate had changed over cosmic history. They expected to measure the rate of the slowdown. Instead, in 1998, they found the opposite of what everyone expected. The expansion of the universe was not slowing down at all. It was speeding up. The galaxies are flying apart faster and faster as time goes on, as though some influence were pushing them, overwhelming the gravity that should be pulling them back together. This was so unexpected that the teams checked and rechecked before they believed it. But the result held, and it earned Saul Perlmutter, Brian Schmidt, and Adam Rees the Nobel Prize in Physics in 2011. The universe was accelerating, and no one knew why. The unknown influence responsible was given a name, though the name is really just a label for our ignorance. We call it dark energy, and the amount of it is the first number that should stop you. Dark energy makes up roughly 68% of everything in the universe. More than 2/3 of all there is, of all the energy and matter in existence, is this thing we cannot see, cannot collect, and cannot explain. Everything else, all the stars, all the galaxies, all the gas and dust, all the ordinary matter that makes up worlds and people, and even all the mysterious dark matter besides, together add up to less than 1/3. The overwhelming majority of the universe is an influence whose nature is a complete open question, and its defining effect is to push space apart. Now, in most models, dark energy behaves as a constant. It is a steady pressure built into space itself, stretching the universe at an unchanging rate. If that is what dark energy is, then the future, while cold, is relatively gentle. The universe would simply keep expanding, the galaxies drifting ever farther apart, the stars slowly burning out over unimaginable spans of time, until everything faded into a thin, cold, dark quiet. That fate has a name too. It is called the heat death, or the big freeze, and it is a slow fading rather than a violent end. But some models allow for something stranger, and this is where the Big Rip comes in. Suppose dark energy is not constant. Suppose it is what physicists call phantom energy, a form of dark energy whose strength does not stay the same but grows steadily over time. If dark energy is phantom, then the push driving the galaxies apart does not merely continue, it intensifies. The acceleration accelerates. And a universe driven by phantom energy does not fade gently into the cold. It comes apart, deliberately, structure by structure, in a definite and calculable sequence. Let me walk you through that sequence, because it is the heart of the idea, and it descends through every scale of the cosmos in order. As phantom energy grows stronger, it would first overcome the gravity that holds the great clusters of galaxies together. Those clusters, bound for billions of years, would be pulled apart, their member galaxies scattered away from one another into an ever-emptying void. Then, as the force continued to strengthen, it would reach inward to the individual galaxies themselves. Our own Milky Way, and every galaxy like it, would be torn open, their hundreds of billions of stars flung out of their orbits and cast into isolation. Then the force would come for the solar systems. Planets would be loosed from their stars, drifting away from the warmth they had circled for billions of years, set free into the dark. And still it would not stop. In the final stretch, the expansion would grow so violent, so overpowering, that it would begin to overcome forces far stronger than gravity. It would overcome the electromagnetic forces that hold molecules together, so that rocks and oceans and any remaining structures would dissolve into their constituent atoms. Then it would reach inside the atoms themselves, overpowering the forces that bind electrons to nuclei. And in the very last moments, it would tear at the nuclei at the center of every atom, pulling apart the protons and neutrons, splitting the fundamental particles from one another, until everything that had ever existed was reduced to a scattering of individual pieces, flying apart into a space that was itself expanding faster than light could ever cross it. Every structure, at every scale, undone, in order, from the largest clusters of galaxies all the way down to the smallest particles of matter. Let me set you down inside those final hours, quietly, the way the physics would actually unfold. Picture a night sky, in that far future, beginning to empty. First, the faint smudges of other galaxies, one by one, cease to be reachable, pulled beyond the horizon of what can ever be seen. Then, the familiar band of our own galaxy begins to thin and scatter, its stars drifting apart, the sky growing darker and lonelier than any night that has ever been. Then, closer in, the nearby stars themselves are pulled away, and a world is left circling nothing, and then not even circling, as it is loosed from its star and set adrift. And in the last instance, too fast to follow, the ground itself, and everything on it, and the atoms of everything, come apart into an expanding dark. It is not fire. It is not collapse. It is separation, carried to its absolute end, everything that was ever together pulled finally and forever apart. Here is where two threads from earlier on this list come back, changed. Remember the false vacuum, the ending that would arrive at exactly the speed of its own news, with no warning at all. The Big Rip is its opposite in this one respect. It is an ending with the longest possible warning. We would see it coming across billions of years, watch it unfold, scale by scale, measure its approach the whole way down. It is the most gradual ending imaginable, and that is its own kind of weight. And remember, too, the strange thread from the very first idea, the life stretched improbably forward past its own midpoint. There is a number here that places all of us on a thread like that, together. Because the scenario was worked out, in 2003, by the physicists Robert Caldwell, Mark Kamiankowski, and Nevin Weinberg, in a paper on what they openly called cosmic doomsday. And for one particular phantom model, they calculated when the Big Rip would arrive. Their figure was roughly 22 billion years in the future. Now set that beside the age of the universe today, which is 13.8 billion years. If that model were correct, then we are not near the beginning of the story of the universe. We are already past its midpoint. We would be living in the second half of the history of everything, in a cosmos already governed, already dominated, by the very influence that will one day take it apart. We must, as always, be honest about the uncertainty, and here the honesty is not merely a caution, but the most interesting part of all. Whether the Big Rip happens at all depends entirely on the true nature of dark energy, and that remains one of the largest open questions in all of science. For years, the simplest and most favored models treated dark energy as a constant, which would give us the gentle fading rather than the tearing. But this is not a settled matter gathering dust. It is a live question, being measured right now. In recent years, results from a major new survey, the Dark Energy Spectroscopic Instrument, reported across 2024 and 2025, have hinted at something that would have seemed unlikely only a short while ago. They have hinted that dark energy might not be constant after all, that it may be changing over cosmic time. Those hints are not yet confirmed, and they may soften as more data comes in. But they have pulled the phantom scenarios, and with them the Big Rip, back into serious scientific discussion. And that is why the Big Rip stands at number 1, above every strange and speculative idea that came before it. Every other entry on this list could, in some way, be argued around. This one rests on a force that makes up more than 2/3 of the universe, that we have directly measured and that we still cannot name or explain. It is the one fear on the list whose outcome is not a matter of philosophy or interpretation, but is being decided, right now, by data, in observatories, by people patiently measuring the light of distant galaxies to learn how the universe will end. To understand why the nature of dark energy is such a deep and genuine mystery, and not merely a gap waiting to be filled, it helps to know just how badly our best attempt to calculate it fails. When physicists try to predict the energy of empty space from the known laws of the quantum world, they get a number. And when they compare that number to the amount of dark energy we actually measure in the sky, the two do not merely disagree. They disagree by a factor so enormous that it is often described as the worst prediction in the history of physics. The calculated value is larger than the observed value by something like a 1, followed by 120 zeros. That is not a small error to be tidied up. It is a sign that something fundamental about the vacuum, about empty space itself, is missing from our understanding. We are surrounded by this influence. It makes up most of the universe, and our theories cannot account for its strength to within a factor with more zeros than there are atoms in a galaxy. That is the depth of the ignorance the Big Rip is built upon. It helps, too, to see the Big Rip in its proper place among the possible fates of the universe, because it is one of 3, and which one awaits us depends entirely on the behavior of that same mysterious energy. Physicists describe dark energy with a single number that captures how its pressure relates to its density, and the value of that number decides everything. If it sits at one particular value, dark energy is a true constant, unchanging, and the universe drifts into the slow, cold fade of the heat death, the big freeze, expanding forever and gently dimming. If dark energy was somehow to weaken and reverse, gravity could eventually win and pull everything back into the big crunch, the collapse we met a moment ago in the omega point. And if dark energy is phantom, if its strength grows without bound as that number crosses a certain threshold, then the fate is the Big Rip, the tearing we have described. 3 destinies, 1 unknown quantity. The entire question of how the universe ends comes down to measuring, ever more precisely, the true value and behavior of a number attached to a substance we cannot see. This is why the recent hints matter so much, and why they have stirred the field. For a long time, the simplest reading of the data placed dark energy right at the value of a perfect constant, which pointed toward the gentle fade and left the phantom scenarios as a distant, unlikely possibility. But measuring that number is extraordinarily difficult, requiring the careful mapping of enormous numbers of galaxies across billions of years of cosmic history. The Dark Energy Spectroscopic Instrument was built to do exactly that, to chart the positions of millions of galaxies and trace how the expansion has changed over time. And in its results reported across 2024 and 2025, it saw something that made cosmologists sit up. The data hinted, not yet with full certainty, that dark energy might not be a perfect constant after all, that its strength might have shifted over the ages of the universe. If that hint holds, and it is still being tested, it would mean the door to the stranger fates is not closed. It would mean the question of the ending is genuinely, actively open, in a way that only a few years ago it did not seem to be. Let me offer the reassurance that the physics itself provides, because it is real and not merely a comfort. Whatever the ultimate fate, the influence of dark energy on the scale of a human life, or a human civilization, or even the entire remaining lifetime of the sun, is nothing you could ever feel. It acts across the vast distances between galaxies and across spans of time measured in the tens of billions of years. It does not tug at you, or at the ground, or at the Earth in its orbit. The stars will shine for ages beyond counting. Galaxies will turn slowly for longer still. Even in the phantom scenario, the tearing belongs to a future so distant that every human concern, every worry and every hope you have ever held will have long since passed into deep time before the first galaxy cluster begins to loosen. The Big Rip is the largest fear on this list, and also, in a strange way, the gentlest to the individual, because its reach is so far beyond us that it can trouble only the mind, never the moment. There is something worth saying about why this particular ending sits at the very bottom of the countdown, beyond the fact that it is the largest, and it has to do with certainty. Every other fear on this list is, in some measure, a matter of interpretation or of open theoretical questions. The quantum immortality corollary is a philosophical reading most physicists reject. The dark forest is one possible answer to a silence that might have gentler explanations. The false vacuum rests on a metastability we are still pinning down, over spans of time beyond imagining. Each can be argued with, held at a distance, softened by an appeal to what we do not yet know. The Big Rip is different in one crucial respect. Its foundation is not a theory we are debating whether to believe. Its foundation is a thing we went out and measured. The acceleration of the universe is not a hypothesis. It is an observation, checked and rechecked, honored with the highest prize in science. We know the universe is being pushed apart. What we do not know is only how the story ends, and that not knowing is the sharp part. Because the ending hinges entirely on the true nature of the thing doing the pushing, and that thing is the deepest ignorance in all of physics. We have named it dark energy, but the name only marks the place where our understanding stops. We cannot say what it is. We cannot say whether it will hold steady, giving the slow cold fade, or grow, giving the tearing. And the instruments, now turning across the sky, mapping galaxy after galaxy, are built precisely to close that gap, to measure the behavior of the influence that will decide the fate of everything there is. It is a rare thing to be alive at the moment when the question of how the universe ends passes from pure speculation into something being actively weighed by data. We happen to be living in exactly that moment. Let me return you, one last time, to the far future, and then let it go. Picture the very end of the sequence, if the tearing is the true fate, not to dwell in it, but to see it whole and set it in its proper distance. The sky long emptied of other galaxies. Our own scattered to darkness. The last star loosed and cold. And then, in the final stretch, the quiet coming apart of matter itself, every bound thing unbound, every held thing released, all of it drifting outward into a dark that grows without end. It is the most complete ending the physics allows, and it is also, and this is the part to hold on to, so unfathomably far away that it lies past the end of every star, every world, every possible concern of anything that lives now, or will live for ages upon ages to come. It is real, and it is enormous, and it is not tonight, and it is not yours. And so we come to rest at the bottom of the list, at the end of the countdown and, in a sense, at the end of everything. It is worth noticing, now that we have walked the whole way down, what these 10 ideas had in common. Not one of them was a monster. Not one relied on anything supernatural, or on any trick of the telling. Each was only a line of reasoning, or a measurement, followed honestly to its conclusion. The unease they leave behind was never manufactured. It was earned, quietly, by the mathematics and the evidence themselves, which are under no obligation to be gentle with us. That is the strange gift of thinking clearly about the universe. It does not always comfort. But it is real, and there is a kind of peace in looking directly at what is real and finding that you can hold it and set it down and rest. So let the scale of it hold you now, rather than trouble you. The end of the universe, if it comes at all, lies billions upon billions of years away, far beyond anything that will ever touch you or anyone you will ever know. Tonight, none of it is yours to carry. The galaxies will drift for ages yet. The stars are still burning. And the only thing asked of you, here, in this moment, is to let your thoughts slow and your breathing settle, and the long quiet of the cosmos become something restful rather than something to fear. Let the vastness be a kind of stillness. There is nothing here you need to solve, and nothing you need to hold. Sleep well, and good night.